No tenía.
No, I don't need this.
Hola, buen día.
Hola,
Mira,
¿Qué pasó?
una pregunta técnica. La doctora quiere dar su plática con su laptop. Entonces, no la vamos a poder transmitir aquí, ¿no? Como lo estamos haciendo, ¿no?
Ok.
Lo único que vamos a poder hacer es con la camarita esta, la vamos a dirigir ahí a la pantalla y que se transmita.
Ah, ok. Entonces voy a ponerlo ahorita en YouTube, en el celular, y ahorita te digo cómo se va a ver entonces.
Sí, ahorita ya está transmitiendo.
Ok.
Mira,
Te digo, lo va a hacer bien en YouTube.
¿Qué tal? ¿Cómo sentiste? ¿Cómo se vio? ¿Cómo se ve?
Bien, se oye bajo nada más. Pues voy a ver si puedo procesar el video y subirle el volumen.
¿Cómo consideras que debemos de poner esta? Ya está transmitiendo. Nada más para allá.
Sí, igual en el puro centro. Ahí va. Pero si quieres voy al celular.
No tiene caso que calentemos la webcam.
Este es otro link, ¿verdad? Es otro link. Porque
Te lo voy a poner ahí. Sí, no, este lo voy a poner ahorita.
la idea es que tenemos que ver si se está viendo bien.
Pero bueno, lo voy a poner ahí. Va a ser el link del jueves.
Tenían, sí, cuando empezamos a organizar, estaba ahí con alguien eran los tres, eran los pretos, más y eran los tres pretos. Después de ese momento, ya entonces, yo sí tenía el proyecto de pagar el proyecto en lugares más tuvieron 6 años
no es porque no había hecho la carta, hoy con la
Sí, sí, la caixa.
Programa de
Sí, sí.
todo tipo y todo programas para hacer más que bueno, de grado de matemáticas y en
Cuando guste. Está mezclada.
Ahí está.
¿Era la camarita, verdad?
Sí, ya va a empezar.
¿El apuntador que me hicieron?
Sí, eso ya lo consiguió la plata. Ah, ok.
Sí, sí.
Sí, los municipios que tienen los grupos de investigación arman muy grande, para mí,
Ahorita la doctora puso el suyo.
ah, bueno. También tengo que saber más.
Ay, no, es un factor limitante. Roberto.
A mí me enseñaron que
En el Zoom, ven para acá, en el Zoom tiene que estar conectado el micrófono de ella, ¿no? ¿Cómo te aquí? Para hacer grande este. Ahí está. El micrófono. Ok. ¿Cuál es ahí? Varios micrófonos. Sí, es varios micrófonos, ¿no? Es este, ¿no?
Sí, incluso si habla se va a ver ahí.
Ah, sí, sí, está bien. Ok.
Ok, sí, ok.
Okay. Okay.
No se puede hacer.
Está apuntando para allá.
Parece que no. Sí, es no me puedo inventar.
Vamos a comenzar la sesión de hoy. La primera conferencia será impartida por la doctora Patricia Casamini. El título es First Principle Study of Structures, Growth Pattern and Properties of 53 School Clusters. La doctora Casamini obtuvo su grado en física de maestría y de doctorado en la Universidad de Calabria. Hizo estancia postdoctoral en química teórica en la Universidad de Hannover. Después fue contratada como profesora de tiempo completo en el departamento de química en el Universidad, en el cual todavía ella está adscrita. Ha supervisado más de 25 estudiantes en sus trabajos de grado, algunos de doctorado, de maestría, y también ha dirigido tesis de licenciatura. Ha recibido a 10 doctores en estancia postdoctoral y pertenece al SNI desde el 2000, actualmente con el nivel 3. Es autora o coautora en 120 trabajos publicados en artículos en revistas internacionales y ha sido coautora también de 20 artículos en libros ya publicados. Ha recibido alrededor de 2.500 citas de acuerdo al ICI Web of Science en relación a sus artículos y más de 3.000 citas, incluyendo citas en libros, en artículos de libros y en otros productos de desarrollo. Las áreas de investigación son aplicaciones y desarrollos en el marco de la teoría de densidad funcionales de la densidad, y actualmente enfoca sus investigaciones en las áreas de metales, cúmulos de metales de transición, diseño teórico de nanocatalizadores, desarrollo de algoritmos para minimización constreñida y búsqueda de estados de transición. Algunas otras particularidades manejadas en esquemas de química molecular o mecánica molecular. Y también ha hecho estudios en el sistema, en melting de sistemas finitos, fusión de sistemas finitos. Estudia las propiedades de estructura de fullerenos grandes y también de fullerenos endoderales. Cedemos la palabra, por favor.
Muchísimas gracias, doctor Álvaro Posada Marías. I will switch now to English. Thank you very much. Álvaro, for this very nice introduction. And first of all, I would like to thank you and all the organizational team for the kind hospitality and for the invitation to be here and for all your effort to bring all of us here in this very interesting meeting on atomic clusters and nanomaterials. I would like just to tell you something because I see there are eventually young people here and maybe, I don't know, students from which are following us. I can also speak in Spanish. It's a Spanish language, what you know. If you like to ask questions, don't hesitate to do also in Spanish. Para los estudiantes que están presentes, por favor que no hesiten también a interrumpir durante la plática y a formular preguntas en español. Si lo desean, será un placer para mí poder dar respuestas. So I'm going to talk about first principle study of structures, growth pattern and properties of platinum trimer CU clusters. This is a work which has been basically developed by a PhD student, Carlos Daniel Galindo Uribe, who I am co-supervising together with an experimental colleague at Simvestaff, Dr. Omar Solor Saferia, who is an experimental professor who works in the characterization, synthesis and characterization of nanoparticles for fuel cell applications. All the work has been developed in the chemistry department of Simvestaff. For the people who do not know where we are located, this is the entry of our institute. Simvestaff is the unit Zacatenco, from which I am part, is located in the north part of the metropolitan area of Mexico City. This is the entry of our chemistry department, and the theoretical chemistry, of which I am being a part of the team since September 1999, is basically located in a known building. The contents of the presentation is as following. I will give a brief introduction and the motivation why this work was of interest for us. I will then talk about the working strategy we have used to try to explore as much in detail as possible the potential energy, the surface of the systems of our interest. I will give information about the electronic extraction method we have employed in terms of all the computational details, and I will present the validation of this electronic structure method in terms of calculations of specific systems, which are prototype systems of the bonding we could have seen in the clusters of our interest. I will go then on the presentation of the results on the most stable structures we have obtained and on some peculiar properties we have computed. Finally, I will summarize the most important results, or some of the most important results we have so far obtained. Well, as a general introduction, let me say that it is well known in this audience that transition metal nanoparticles, especially during the last decades, have attracted a lot of interest and attention in different fields of nanoscience and nanotechnology. One of the most important fields for the study of this system is the field of catalysis. And this is because nanoparticles have shown to be systems having the great advantage to present large catalytic areas and very important reactivity properties. In between all the big jungle of possible nanoparticles, platinum-based nanoparticles have been used as catalysts for many reactions. And in between all of these, ones of the most important are oxygen reduction reactions, abbreviated as ORR, which is one of the most challenging. Yesterday, in the talk of Dr. Alonso, you saw a very beautiful introduction, actually, of how a fuel cell works. Of special importance in between all these platinum-based nanoparticles, in the last few years, in the last decade or a bit more than a decade, of special importance results to be the PT3-Cu alloy, for which it has been demonstrated that on depending of the morphology this alloy can have, that means on depending of, if you like, of the shape these nanoparticles can have, it can present better stabilities than the pure and much more expansive PT catalysts for fuel cell applications. Now, for fuel cell applications, the best catalyst for excellence by excellence is considered to be the platinum, the pure platinum-based catalyst. But the platinum elements, as we know, is an element which is quite scarce in the platen. It is very expansive, and for this type of applicability, is also an element of low durability. So what has been done over the years is to try to somehow design and then synthesize and characterize a platinum-based nanocatalyst with the aim to reduce as much as possible the amount of platinum, substituting the rest of the atoms with much less expansive elements. These are generally elements which belong to the 3D row of the periodic table. And so to have basically, with the idea to obtain basically nanocatalysts which are cheap, which are of much more high durability, and on which the platinum concentration is very low. And the best situation is when these are basically nanoparticles, core shell often structures, in which the platinum basically decorate the external part of the nanoparticles, and the rest of the cheaper elements stay inside it. Well, experimentally, as I told you, because as I told you, these PT3 CU nanoparticles it became quite interesting in the last decade or so. I would like also to say that experimentally those have been found in different shapes. So depending the shape, different shape can come on depending of the synthetic methods which is used for their productions. Of course, on depending of the shape they have, and this means on depending of the possible phase area, so phase which they can have, they can present different catalytic activities and stabilities in various reactions which they are applied. In between all of these groups in 2015 have found that this kind of PT3 CU nanoparticles can be synthesized and characterized in icosaedra and octaedra shape. And actually they found nanoparticles of this type of just a few nanometer size. They produce these particles of very few nanometer size. Here you can see in this cut of this picture of this one of these papers that they can be produced in the range of few nanometers, and they can have either icosaedra or octaedra shape. But the problem here is which kind of nanoparticle morphology is the most stable between these two is an unclear question so far. And moreover, there is, or at least there was not any information at the time we started the work, was about 4 or 5 years ago, of how these nanoparticles are formed on increasing their system size by adding, if you like, at a time, a PT3 CU unit. And moreover, there was no systematic study at all to elucidate these structures at an atomistic level. But on the other side, it is also very clear that over the last decades, theory has demonstrated to be very important in the design, in the prediction of peculiar structures of nanoparticles which have been then synthesized, characterized, and used for specific applications. So theory is very important for the design of this type of systems, which could have a very important potential applications in many fields of nanoscience and nanotechnology. When we started this work, of course, we went to the literature and we made the literature search, and we noticed, because we want to know if eventually this kind of theoretical study, which we aimed to do, was already done, or if there was something available. And what we found, there were just few works, they are cited here. In between this, I would like to discuss a bit about the work made by JUEVES and collaborators. This is a density functional theory based work. What these authors basically did is they had the pure copper, they studied pure copper and the pure platinum clusters, and then substituted from these homonuclear clusters one atom of the other species at the time. They came up to study this kind of cluster range sites with different compositions. In between all of these are the 3 cluster structures of our interest, by meaning of the PT3 CU unit, of the cluster of PT3 CU formed with 2 PT3 CU units, and the one formed with 3 PT3 CU units. Here in this paper, the copper atoms, sorry, now they are a bit overlapped to each other, maybe it's the projector was not so in my presentation. The copper atoms are depicted with red bubbles and the platinum atoms with silver color. However, in this work, there was no given information on the spin multiplicity of these clusters. This was one thing we want to understand. And also because, as I told you, how the work was performed, on this specific composition of the clusters, there was not done a systematic exploration of their potential energy surface. So with all this, and then there was also other works done also here by Professor Posada and collaborators. They also studied the different clusters which are obtained by a combination of different concentration of platinum and a copper, but they studied with other purpose. They absorbed on some cerium oxygen surface, or they made some reactions with that. And of these systems they published here, the one which was of our interest was the PT3 units, which we have no problems of comparison, neither in the structure and neither in the spin multiplicity, and so we discuss later. So with all this background in mind, our study started, and our focus was to give an answer to the following listed equations. First of all, we want to understand which are the most stable structures of these compounds with this specific composition. The second equation was, what about the growing mechanism these clusters might have? Because remember, the important question was also, this also from an experimental point of view, which are the most stable structures, the ones which present eventually an icosahedral moiety arrangement, or the ones which present an octahedral arrangements of the atoms. We don't know, we need to know, we want to understand this. Then the other thing we want to understand is, because our work, and I will explain this in details also successively in this presentation, was performed in the following way. We optimized the first and studied the first in detail the smaller size of these clusters, and then to study the successive ones, we had the PT3 unit at the time to the previous already studied most stable structures, and then we made the procedure to obtain the most stable structures of the largest cluster size and so on. And so because of this, we want to understand if during the growing good clusters, the PT3 units would have been maintained or not in the final resulting structure. We want also to understand what is the copper and the platinum atom distribution in these systems, because as I also told you before, there was no information on the atomic of how the distribution of the atoms is really looking at this from an atomistic point of view. And finally, once we would have obtained the most stable structure, our questions were also related to try to understand how properties might change by increasing the cluster size of these systems. So with all this in mind, we started the work. The work was performed taking the DEMON2K program. The DEMON2K program is a density functional theory basic program. It's a program which is free of charge for academics. If somebody is interested to use it, you can go just at this link and contact us, and you will get the full source of the code. The DEMON word stands for density of Montreal, where the code was originally developed, and then over many years ago, and then over the years, it was continuing the development in different groups all around the world, and one of the main groups where the code is now developed is the group of Sinvestat, thanks to Dr. Post, who is here present, and all the collaborators which are involved. And the DEMON2K communities is a community which is continuous development since more than 20 years. And there is basically every year meeting, and the meeting of this community goes in different parts of the world. During the pandemic, we could do meetings only online. And here I would like to show you just a couple of pictures of some previous meetings. This was a meeting actually we have organized, the Mexican teams in Los Cabos in 2014. Here you can recognize some people you already know, and many others. And this was one of the meetings that we had in Canada. The last meeting last year was again in Canada, but in Alberta. And once again, if you are interested in looking at this code, go to this web page and then simply contact us. Well, now about the working strategy. How we have, which working strategy we have employed to try to explore in details as much as possible, if you like, the potential energy surface of these systems. During the talks we have listened in this yesterday, we saw there are many ways people can use to explore the potential energy surface of the system. One can use genetic algorithms and many others, if you like. There are many other possibilities. For us, in our group, theoretical group, similar stuff, it has been turned out during the last decade or so that a good working strategy is to explore the potential energy surface in the way I'm going to describe you in a moment. First of all, what is a potential energy surface? It's just for students. As we know, it's a multidimensional function which can present very critical points between minima, maxima, and transition states, as we can see in this sketch of this picture here. But from a theoretical point of view, if one wants to study reactions, we know that only minima and first order points are of interest because they correspond to stable isomers, this be the minima structures, and to transition states respectively. And of course, what is the problem here is that as the system size increase, the number of minima, of course, will grow. So the problem can become a much more complex problem than having to study a system with just a few atoms. Well, when we use, what is the strategy we use? What we do is the following. For each cluster size, we run different Born-Oppenheimer molecular dynamics simulations. And along these trajectories, we pick up systems, structures, from which then we start a full geometry optimization without any restriction. And these BOMD simulations are done considering the system in different spin multiplicity and different temperatures. Why we use the BOMD? Because basically we know that in this way, all the initial points from which then we will start our geometry optimization are generated on the potential energy surface of the cluster. This is a method which is simple. It has given to us the information that we can explore better the potential energy surface of these systems. And as I told you, we have worked with this kind of working strategy now since several years, and we have noticed that it's been very successful in the study of different system types. Here, I cite some papers where you could see we have worked successful in the exploration of the potential energy surface of systems like alkali metal clusters, different mixed transition metal systems, bismuth oxides, molybdenum carbides between the others, and so on and so on. So we know this works relatively well. So as I was telling you before, how we explore the potential energy surface of our system of interest with Born-Oppenheimer molecular dynamics is basically indicated in this picture. As I told you, we do beyond this simulation at different spin multiplicity and temperatures, and along these created trajectories, we extract the geometries of some structures. These are the initial structures for our successive geometry optimizations. And by doing this, because we have studied different PT3CU cluster sites, and we have optimized several dozens of structures, as you will see in a moment, without any restriction in this work. The lowest energy structures have been then characterized by analytic frequency analysis in order to discriminate between minima structures and transition state structures. So, going to the computational details, these are the informations of the electronic structure method we have employed in all our study. We use the linear combination of Gaussian type Con-Sham auxiliary density functional theory as it is implemented in the DEMON 2K code. And here there are other informations about the functional we used. We have done the work at the GGA level of theory. These are the orbital base sets which we have used for the copper and the platinum atom respectively. And here are a few more details about these computations. So what we studied, the systems we studied are system of PT3CU type from one PT3 unit up to systems which were initially built with 11 PT3CU units. We have explored for each system size several spin multiplicity by means of the starting with the multiplicity of singlet up to the multiplicity of octet. And the molecular dynamics trajectories we have created in order to pick the initial structures for the successive geometry optimizations are characterized by these details. They were 20 picoseconds long, and we have used a different temperature for this, because what is the idea here is to give to the system somehow the freedom that the atoms can move and the structural arrangement can change, but we also don't want that the system eventually breaks in parts. And so we took care to that. Now, this is the electronic structure method, and I would like to point out something before to proceed to show results. What are the expected errors within this methodology, which we could expect? Because the fact is we had to predict then structures and properties of systems which were never studied before at certain system size. Well, the expected errors in auxiliary density functional theory using GGA functions are that the geometrical parameters are expected to be within plus or minus 2 picometers with respect to the bond distance, basically with respect to the experiments, and bond energies are predicted to be between 5 and 10 kilocalories per mole with respect to the experimental results. This method has been by us validated before to proceed to the study of the clusters of our interest. And how we validated it? We validated this method by making calculations of bond lengths, frequency, dissociation energy, ionization potential, and electron affinity for 3 diatomic systems, which are copper dimer, PTTCU dimer, and platinum dimers, from which reliable experimental data are present in the literature. And so you can see here, by comparing the theoretical values we have obtained with our method and the experimental available data, that there is good agreement between the experimental and the theoretical results. This validation gives us the information that the electronic structure method, which I showed you before, is good enough to be used to perform the calculations of the clusters of our interest. And as I told you, we have done a very detailed exploration of an extensive study of to find the minimum structures of these clusters, which were built initially with 1 to up 11 PT3 CU units. Here in this slide, I want to just show you, as I said, several dozens of structures have been optimized, and several minima structures have been found. And here I would like to show you in these slides the isomer distribution in relative energy of all these studied cluster sites. Here in this picture, this relative energy in between all different stable isomers we found at each cluster sites are given in electron volts. Each line here represents a different isomer, and this each color represents a different spin multiplicity. Please.
What is the reason of such a wide distribution in the case of n equals 5? Because this is the widest distribution.
Yes,
Yes,
I was going to comment on that, because these clusters at these sites were never studied. We want to do a very detailed explorations and go to because we studied different spin multiplicity, because we picked along with the BMD trajectories different initial structures. We found, of course, for each cluster sites different isomers, so different cluster shapes in different spin multiplicity. What we know, as you were pointed out, is that in some cluster sites, we see the relatively isomer distribution can be much less dense than in other cases, as we see, for example, for the case of clusters initially built with 2 PT3 ACU units, or 4 or 5, as you pointed out, and so on. But of all this, now, the most stable structures result to be the ones which you see in this slide here, where in this study we depicted the platinum atoms in silver and the copper atom with red bubbles. In the slide, you also see in green this number n, which represents the number of the PT3CU units with which each cluster size was initially built. In black, you see the obtained the spin multiplicity, which each of these most stable structures at the end possess. And we notice that in some cases, like in the case of the clusters which were initially built with 7 or 8 PT3CU units, we found two identical structures as depicted here, which were isoenergetic to each other with two different spin multiplicity, by meaning in this case of the multiplicity doublet and quartet, in this case of the multiplicity triplet and quintet. Also in blue, you can see the approximate size in nanometers, excuse me, please, I have to go back. In nanometers of each of the cluster structures we studied. And you can see that with the electronic structure method I have shown you before, we have optimized clusters larger than 1 nanometers. As I told you, the most stable structures were identified by frequency analysis calculations. And because I will go to this in a moment, but I want to point out here, to open here a little bracket to show you, people can ask why it was important eventually to use the BOMD to try to explore in details the potential energy surface of these systems. As I've shown you before, there was a work done by these authors in which 3 structures of the clusters of our cluster size of the systems of our interest have been already reported. And these are the ones you see here. These were what we found in the literature. By making the work we did with this type of exploration of the potential energy surface, as I showed you in the previous slide, these are the most stable structures we found for this corresponding cluster size. For this system here, the one with just 1 PT3 units, you see in terms of the structure, there is no problem. We find that in both cases, this kind of tetrahedral type structure. Here we have characterized this also with the spin multiplicity. In the work of the group of Dr. Posada works, there was no problem. They gave the spin multiplicity was doublet, so we agreed with that. But then from that side on, there was only this work here in terms of larger cluster size of our interest. And these are the structures which have been reported by the previous research group. In our work for the PT3CU2 cluster, we found this structure here as the lowest energy, stable energy structure with a multiplicity of triplet. And we can compare with this one here. We see already that there is a different cluster arrangement, but the thing is, we also studied this structure with different spin multiplicity, and the lowest we found is high of 0.13 electron volts with respect to the one we found. So we found a more energetical stable structure in our study for this cluster size. And the same occurred for the study of this cluster size, where the system was initially built with 3 PT3CU units. We found this structure here in multiplicity of quartet. The reported structure is this one, and it is ion energy of now 0.2 electron volt with respect to the one we have found. So this is only to show that it's very important to try to study in details the potential energy surface of systems which were not studied before, because especially when we have a combination of different metals of this type, a lot of structures can be formed. They might be, they lie energetically very much close together, and well, one can really miss a minimal structure which can be deeper in the potential energy surface. Please, Giulio.
The comparison that you have made with previous calculations, do the two types of calculations using the same exchange correlation.
Yes, and this is the point, because thanks for this very nice and important question at this point, is done with a density functional theory and with the same PBE function. So it's a GGA approximation as well. And but I said from the beginning, the working strategy these authors used was different from ours. They started from the homonuclear clusters, and they successively have changed eventually, if they start from the platinum clusters, they changed the copper atom type at the time, and the same from the other side. So the exploration of the potential energy surface for this PT3 CU based clusters was different, but you see that is really important due to the energy difference. We are talking about electron volts here. These are not kilocal or kilojoule, so it's a huge energy indeed. See, the method was basically the same. So let's go back to the questions. What were the questions? Which are the most stable structures? So far, we have given answer to these questions. I told you we have characterized this by frequency analysis. And because these clusters at the certain, starting from a certain cluster size were never studied before, we decide, because there is also an experimental part of the work going on, which I will talk in a moment, we want also to characterize a bit better the structure, so we calculated the frequency analysis. I show you in blue here the first frequency analysis for each of these calculations, and you can see that all calculated first frequencies are real, and therefore the clusters are minimum on the potential energy surface, on the corresponding energy surface of each cluster size. But also because we had the calculated the frequency, we could do something else.
It seems to me that from n equal 4 to above, it is a small fraction of an FCT crystal. Is that right?
Yes, I will go to this in a moment, because if I'm no, we never talked before, but this is an important part of the talk. So let me continue. I will satisfy this question, and I open details. Okay, so we could do, thank you. We could simulate the ER spectrum. I will show you all the ER spectrum quite fast of the smaller clusters up to the largest one we studied. Please notice that all these spectra basically present active IR peaks, which are in a very small window of energy between 0 and 200 wave numbers. As you can see, we can grow with the system size up to now. We are here with the clusters formed initially with 9 PT3 CU units until the largest one, which are the ones formed with initially 10 and 11 PT3 units respectively. Well, briefly, what I can say, I go back a moment. We noticed that there are some characteristic things in each of these. In some cluster size, we have eventually just one main intense peak. In others, the density of the active peaks increase, and they can be a bit different from each other. If we look maybe just with more details at the simulated IR spectrum of the largest cluster size, we can see that just by changing the cluster size of one PT3 units going from 10 to 11, we see that this spectrum here of the corresponding cluster, which was initially built with 10 PT3 units, result to be a bit more dense with respect to the ones which was built with the largest number of PT3 units we have studied. Well, this kind of results can serve eventually, we hope, as a guide for future work, which might be made also experimentally on these systems. One thing more I would like to point out at this point for the part of the frequency analysis calculation we did, quite surprisingly, these systems do not have random activity, none of them, but they are only resulting ER active. Well, so far so good. Let's go. The other question was, what about the spin multiplicity of these systems? Well, I can tell you something more about this. First of all, looking at the spin multiplicity, we can say that in general, these clusters prefer relatively low spin multiplicity, if you like, and the multiplicity of triplet is seems to be preferred for clusters which were initially formed with an even number of PT3 units, as we can see here in the case of the ones formed with either 2, 4, 8, or 10 PT3 units, whereas the multiplicity of quartet seems to be the preferred spin multiplicity for clusters which were initially formed with an odd number of PT3 units, as we can see here for the case of clusters formed either with 5, 7, and 3, okay, PT3 units. So also this question somehow we could solve and give an answer. The other question was, what about the PT3 unit itself? What happens when the cluster size increases? Is this PT3 unit maintained in the final resulting lowest energy structure or not? Or not? Well, we can see very clear. This is the PT3 unit, which was the most stable one, and we can see that as the cluster size grows, indeed, this is not maintained. But we can see without any doubt that the cluster structure results to be from the from the arrangement of the atoms involved in the structure. And so this is not preserved as the cluster size grows. And now we go to answer the question of Dr. Faustino in details about the ground pattern. This is something we found really interesting, and I would like to share this with you in details today. Well, we noticed that by drawing the cluster size at the smaller cluster size, basically we cannot say so much. We see that, okay, seems that the platinum wants to go more outside, and we notice already that the copper atoms at a certain point might be like to be are more friendly between each other, try to occupy internal position of the clusters and to be more close to each other. But what we notice is the following. At the stage of the cluster formed with the initial number of 4 PT3 CU units, a kind of square based by pyramid fragment was forming, as you can see here. Please remember one thing. As I showed in the experimental work, it is not clear which one of the fragments are preferred in the growing of these nanoparticles. Is the icosahedra or is the octahedra? So we see this pattern here. What we notice then is this pyramid, square pyramid fragment. It becomes a full octahedral fragment as we grow the cluster size just by 1 PT3 units. And that this now full octahedral fragment is formed with 90 atoms, as you can see here. At the stage of the cluster initially formed with 6 PT3 CU units, this octahedral fragment is conserved, as we can see here. What happened then? Then we grow the clusters of 1 more unit at the time. And we see that the cluster growing now occurs along one direction with the formation of twinned octahedral moieties, starting from the cluster size, which was initially built with 7 PT3 CU units. Now, in the experimental work of these 2 Chinese groups, which I shown before, they were saying that the formation of twinned moieties could occur in these nanoparticles, but they could not really see clear this. Here we see that indeed the formation of this kind of twinned moieties can occur, and moreover, the cluster can grow, continue to grow even more along the same direction as 1 more PT3 unit is initially added. We can see here now that we have 3 of this moiety along one direction. What happened after that? Well, what happened after that is really interesting. At the stage of the cluster initially shown with built with 10 PT3CU units, we see that a big octahedral fragment starts to be formed. It is like what occurred here at this stage when the cluster was initially formed with 4 of these PT3 units, and then the full octahedral moiety is completed at the stage of 11 PT3CU units, which means to the cluster which is built with 44 atoms. Remember, the first octahedral moiety was built with 19 atoms. And now if you ask people who work a lot in cluster science, especially theoretical work, they know very clear that at the stage of 19 atoms and 44 atoms, we can build eventually octahedral fragments, because there is going to be magic numbers for the building of this octahedral fragment. So what we see is the following, that on the drawing of the cluster, we notice the formation of octahedral, twinned octahedral, and then again of octahedral moieties which are observed. Now, coming back to the cluster size, these are cluster sizes which are very large. We went over 1 nanometers, and we can see, in order to bridge now once again with the experimental question, what are the most stable structures, the icosahedral or the octahedral. At the using the electronic structure method we have employed here, we see that at least up to the nanometer, we don't see the presence of icosahedral moieties, but that the preferred moiety is the octahedral. Eventually, to build moieties which are icosahedral, the cluster size, the cluster should grow not only in one direction, but also eventually in another direction to allow the formation of this, if you like, pentameric base on which then the icosahedral structure should be built. And one thing which was interesting, we found this really interesting, but one thing we found also interesting, this was recent, because Carlos Daniel really searched the literature to continue, which was for us really interesting to see.
What about the tetrahedral shape?
No,
Tetrahedral shape. What about the tetrahedral shape?
This one.
No, you know, in any age,
yes,
on the edge, on the white,
yes,
spot,
yeah,
you have a tetrahedral shape.
This
what about to having tetrahedral array?
Okay, this is also an interesting question. We have not explored this in detail. We see that indeed the tetrahedral moieties are present, okay? And especially at certain cluster size as the one you pointed here. But this exploration in this direction of exploring
because there are also magic numbers in the case of the tetrahedral.
Yes, what we are going to do, I don't want to anticipate, there is still a lot of work to be done in this. Carlos in the moment is working to look, because we want to really to see in more details eventually the coordination of which type of atom with respect to the others, is going to do a critical point analysis on this and other type of analysis. When we will have eventually the results, we could answer more clearly to this question. In the moment, we can only speculate that yes, these tetrahedral moieties are present. We see in some cluster sites, but we need also to have this information of the coordination numbers to give a full, clear answer to your question. Thank you. So, and I was telling you this, we found really interesting, and Carlos searched the literature continuously. Before I came here, we were discussing a lot in my office, and he came actually with this paper. Indeed, he told me, look, Doctor, here I can show you something in which I have noticed that this type of glow pattern has been already found in other type of systems. And indeed, this experimental work done by Carlo Ajibei and the collaborators was published in Angevant in 2007, in which the authors experimentally have seen and published this paper titled Chemical Sharpening of Gold Nanorods, the road to octahedral transition. So what they do experimentally, they were able to grow clusters of gold. These clusters of gold are growing in one direction. You see here, these are, there are no the size here, but it can be found this in the paper. You see here these tips here. this shape resembles quite nicely the shape of the cluster we found of this type of composition, which is completely different from gold. But let's look at the shape now. This was our cluster initial build to 59, 53 CU units, and then at the point, the cluster continued to go and goes to an octahedral structure. I found this interesting. I just added this at the last moment before to come here. This
Are the red points within a plane?
some yes, some not.
Okay.
Yes, some yes, some not. Actually, this cluster here is one of the ones which we found with higher symmetry. This is a kind of C2 with respect to many others which which have a very low point.
Perhaps as a reference
Yes.
point, this kind of compound,
Yeah,
I assume it exists also as a biaxis.
see, yes.
What kind of structure?
Yes, I have a picture later on, but because you are asking me the questions now, I will answer. It has been detected actually in many parts of the planet, in Japan, in Alaska, in Brazil, and in parts of Africa. I have the slides at the end, I will go to that, because I just put this yesterday because Julio asked the question to somebody else related to this for other structures. And I was really searching for that. And it was given a kind of FCC crystal structure, but wait, there is a point. In these FCC crystal structures, they found a lot of iron impurities. Very recently, and so they, and now I'm not sure that this was correct, in fact, because in 2019, I have the slides just at the end, I will show you before I finish. It was published in another paper in the One Mineral Journal by a group in Congo. They found this compound, they detected crystal structure by X-ray, and it resulted to be a kind of okay, I should go there. Can I go there? Because it's orthorhombic. It's orthorhombic. Yes. So, but I will show you. It has been registered in the table of new minerals, etc., as in this crystal structure. But still, there is a kind also of impurity there. I will show you in a moment. But there, the impurity is only between the percentage of copper and platinum atoms in the unit cell. We will see this. It's quite interesting. But let me now continue. I hope I have answered your question. And the last question, what was about the structure? What is at the atomistic level? Okay, the PT3 units is not maintained, but what about the rest? You remember what I said, and was also mentioned in the other talks in this meeting. What one wants to do when wants to create a new nanocatalysts which are efficient for this type of applications is to reduce as much as possible the most expensive element, which is platinum. And eventually the idea is that the platinum covers, decorates the external part of the structures, and that the cheaper element stays inside. So what we see here that as the cluster structure grows, it seems that indeed the copper atoms try to occupy preferentially in a position of the cluster structure, and as much the cluster structure grows, they try to be more close together, and that the platinum indeed are the atoms which stay more outside the structure. So as the cluster size increases, the copper atoms prefer to stay close together. They are really friendly atoms in between each other. So now, last part of the talk, let's go to the properties. What properties we calculated? Well, we looked at several. We calculated the spin magnetic moments per atoms of these low energy structures I've shown so far. And we see that this is here given in Bohr magnetons with respect of PT3 units, numbers with which each cluster size was initially built. Then we see that this property basically decrease from n equal 1 to n equal 6, then increase again, drops again at n equal 9, and then increase again. Also, I want to say, it was not only done a study on the neutral systems, but because we want to calculate the properties also and to understand like ionization potential, electron affinity, but also we want also to understand if eventually by taking out one electron or adding one electron to the cluster, what would happen in the final cluster structure of this positive and negative ionic species. We calculated also the cationic and the anionic clusters. Here, and then we calculated the spin density of all the studied species, because we want also to understand where the unpaired electrons have been eventually allocated in the structure. So in this slide and the following one, I'm going to show you the results of these spin density calculations which have been done. The pictures are a lot, so they've been separated in cluster size from n equal 1 to 6 in this slide, and the next one for the larger clusters. And we can see, if we just compare the cationic and anionic cluster structures with respect to the cluster structures of the neutrons, which we saw before, basically the change of the charge doesn't really change, as you can see, the cluster structures. And what we can see is that you see also the spin multiplicity here of the anionic species. We see that basically the spin density is most allocated on the platinum atoms. The same occurs for the larger cluster size, as we can see in this picture, where now the spin density results are shown from the cluster size, which were initially built with 753 units, up to the cluster size, which were initially built with 1153 units. And well, we calculated also dissociation energies of these systems. Here the results are given in electron volt with respect of the cluster size. And we calculated this property into ways, because we want to know how much energy one should give to the system if we want to basically reduce this in atomic contributions, or if we want to reduce this in PT3 CU units. Both results are given here. The dissociation energy per atom is given with this kind of rhombus symbols, whereas the dissociation energy per PT3 CU unit is given with these squares symbols here. And we can see that in both cases, the dissociation energy increased with the cluster size, and that the increase of the dissociation energy per atom is more moderate with respect to the one of the dissociation energy per PT3 CU units. We are going to conclude. How much time do I have? How much time? Okay.
The next one. We are over the time of the next.
Okay, I stop here. I stop here. Okay, so these are the ionization potential and the thank you so much, but really, if it's a joke, I go to simply can stop. Thank you. These are the ionization potential and the electron affinities results, together with the difference of these calculated properties. Here are the adiabatic results, and here are the vertical energy results we calculate, and we can see the trends. The ionization potential decrease, the electron affinity increase with cluster size, and we can see the behavior of the difference between these two properties. And indeed, I was not joking, I was just on the way to conclude. These are the main conclusions of the presentations. I have basically talked in very much details in all of these points. I want only to remark this fact here, that we see from this investigation we did, that there is the formation of octahedral and twin octahedral moieties, which is observed for the most stable structures. Why I'm emphasizing this? Because at the moment Carlos is working in the synthesis and characterization of these nanoparticles. He's doing this experimentally. And he has been able to synthesize these nanoparticles in a range between 14 nanometers and 30 nanometers. And from the first time images he got, he sees the deformation of octahedral structures, fragments of nanoparticles is indeed there. So he's still working on this, but this is a very good results. I would like to show you. Here's Carlos. He's really a very brilliant student. Dr. Marcelo Sapere is the co-director of this thesis. I would like to thank the research group and all the members with whom I am collaborated in Mexico and abroad, foundings and agencies which have supported me and continue to support our group over the time, and doing this very much seamless and harnessed in the Demon Developers community, and of course you all for your kind attention. And I will leave this slide here because it was going to the question you had. If you like, we can discuss a bit more. I am waiting for your question. Thank you.
Could you please go backwards at least 3 or 4 slices? Keep on going, keep on going. There. Well, that could also.
This one?
This one or the previous one, it's okay. It seems to me, to my eye, that it is going to shell-like structure.
Yes, absolutely.
But nevertheless, there must be another transition in which it switch from core shell to L12 or L10. I don't know. Do you have any idea when you will be establish the order?
No, we don't, because of course we should go probably to larger system size, but we see exactly what you are saying. It seems so. I was trying to emphasize this during the discussion, that because the copper try to be together, we believe that drawing this, and then we will have really a kind of the core shell formation, but we cannot exclude the other possible transactions.
But the other thing is, there is a very simple way to estimate the state of order of these nanoalloys. If you do the contabilization of the different pairs that you have within the system,
yes,
and you calculate the homo pairs minus the hetero pairs and then normalize, if this goes to positive or negative values, it is at least you can have a flavor of if this is an ordered structure or segregated structure.
Yeah, this can be done. Thank you. Of course, I said this is just the part of the results we have obtained, which we are relatively sure, but there is a lot of work which is still in process and much more which can be done. Thanks.
Let's give the
We can also discuss later. Thank you.
other questions.
Si los estudiantes quieren, también en español no hay preguntas estúpidas, por favor, señor. Gracias.
Are you sure that this is a core shell effect, or just the fact that you have 3 times more platinum atoms on copper?
That is also absolutely the percent. It's very important too, because of course to have more platinum, the zero is quite. Let's say, let me try to explain this with the right words. It's not surprising here because we have this proportion 3 to 1. So a copper atom is smaller. It works against 3 platinum atoms at the time. It is relatively easy that the platinum tries to encapsulate, this. Yes, absolutely. The proportion plays a role, which is very important. We saw yesterday in another talk there was something which I think rhenium and palladium, there the percentage was a bit different, showing some structures, and of course we'll never cure such effect there because of the atom proportion. Thanks.
Okay, some students have a question. Okay, we appreciate your nice talk.
Thank you very much.
The next presentation will be given by Jonathan Lucas Ceballos, the title of this talk is Theoretical Study in Structural and Hierarchical Properties of amino acids interacting with metal structures. Le daremos unos minutos para que preparen la presentación.
Aquí se llama perdón.
Ahí sumar. A ver, tú.
Ahí está ya, mira. Ya está. Sube y baja, ¿te fijas? Ya está
Sí.
activado. Ok. Déjame abrir el. Esto
Ah, ya apareció.
sí,
Sí, mira, varios
Sí.
micrófonos, Intel, ok,
está bien.
ok.
Y aquí se está moviendo.
Ok, entonces lo que tenemos que hacer ahorita es share screen, ¿no?
Ujú.
¿Y cuál va a ser?
Esto es lo que se va a ver, acuérdate, en el.
El screen va a ser este screen.
Es una sola pantalla, ¿no? Sí. Déjame ver.
Ok. No, la apuntador. Acá lo tenemos. Hay que poner la cosita. Roberto, ¿se ve bien todo?
Hay que hacer nada más, te ven las dos pantallas.
Está al revés, un poquito. Ahí está. Sí, ¿verdad?
¿Te vuelve a la izquierda?
Sí. No se sigue viendo el modo presentador.
Seguro. Espérame. Yo creo que apreté el botón correcto.
Sí. Ahí está.
Ya,
Ya.
¿Y el sonido? Puedes ponerte el micrófono. Te va a limitar el radio de acción. Si no, pues,
Sí.
Bueno. ¿Sí? El de ley.
Bien, podemos continuar.
Ok. Bueno, pues muchas gracias al doctor Álvaro y al comité organizador por la invitación. Now I will switch to English. I will try to switch to English to make this presentation on the theoretical study on the structural and optical properties of amino acids interacting with metal clusters. Right now, I'm working in the group of Ignacio Garzón as a postdoctoral researcher. So it's kind of work that we are developing the last years. I will start with a brief introduction in where I want to talk about chirality, amino acids, and antispecific recognition. And then I split in three the main objective of the metal nanoparticles interacting with system in this case. Well, in the first case is about the conformational absorption. Then I want to talk about the metal ligand interface optical activity. And finally, the interaction mechanism and interface configuration. And then some perspectives and work that we are performing right now. Well, as introduction, the chirality is a property that some materials and more organic molecules presents, well, it's where it's like the right and left hand. You can superimpose both hands, and this is the property that is associated and is presented in some medical molecules like penicillamine and tambutol. And the properties of the enantiomers
it's very different. For example, in the case of penicillamine, one enantiomer is for the treatment of the arthritic, and the other one is on tackling. So there's another case where one enantiomer is used for the nauseas of the pregnant women, and the other enantiomer makes mutations on the baby. So this is why it's important to study this area. The principal way to observe the chirality on the materials is using a circular decrease, where you incite light on the material, circularly polarized. In this case, this one it's an example of an absorption spectra of two different enantiomers, where you can see it's very similar. So it's not a clear observation of a difference here. But on the bottom, you have the circular decrease of these two enantiomers, where you can see this one going up and then down. It's one enantiomer, and the mirror image, it's the other enantiomer. The chirality can be the chirality can be obtained in three ways. On the shape of the nanomaterial or the molecule. Also, it could be obtained by the assemble of the material, like this one, in where you have a carbon nanotube, where you put something. This one gives an helical chirality. And the other one is induced by ligands, which is the one I'm going to talk. Another way, theoretical, to measure the chirality of the materials is the Hausdorff chirality measure. This one is a geometrical measure, where I don't remember exactly the variables there. But this one goes from 0, and if you're going up, the material is more chiral, and if it is close to 0, the material is achiral. Then we have a family of 20 amino acids, where the only one with doesn't exhibit chirality, it's the glycine. The others ones exhibit chirality. In this case, we focus on this one, which is cysteine in our work. The amino acids are widely studied, interacting with some other materials like this graphene quantum dot, and this kind of cluster, and also the fullerene. And also the combination of some amino acids brings what is called the peptide, and then the combination of peptides brings us the protein. This one, I put this one because sometimes we make a misunderstanding between absorption and absorption, where the only difference is this zero. So the absorption is when the material stay on the surface of the absorbent, and in the other way, when you have absorption, you get into the material, well, I don't know if I make a mistake, but it's like a defect, in this case. So in our case, we are exploring the absorption of the material, where the material stays on the surface. Also, we have the molecular recognition, where mostly it's going to be the existence of some van der Waals interaction, some non-covalent interaction, where you have van der Waals and hydrogen bonding more commonly on there. And this will bring us what is called an enantiospecific absorption, where you have an absorption that have the discrimination between chiral compounds. In these two works of Pelayo and Xochitl Lopez, you have this case, it's the one that is a combination between a chiral gold nanoparticle and a chiral molecule, where you can have 4 different combinations. But these 4 different combinations between the 2 enantiomers of each one brings us only on 2 different possible absorption. Since the absorption of LL and DD is going to be the same, and the LDDL enantiomers is going to be equivalent. Well, then I want to talk about the 3 papers that we published recently, where we studied metal nanoparticles interacting with cysteine. In the first case, where the main objective was the conformational absorption, it's a gold nanoparticle interacting with cysteine. This molecule was experimentally synthesized, and it was around 1 nanometer, 2 nanometers of size. In this image, you can see the hand image of the gold nanoparticles interact after the incorporation of cysteine. And here is the interesting thing. These 2 are the cysteine Raman spectra, where you can see which is the principal peak observed about 2,600 wave number, and it's associated to the SH stretching. So when you incorporate the cysteine to the gold nanoparticle, this peak disappears because the interaction with the nanoparticle is expected to be bilateral with the formation of an sulfur gold bond. Then from there, we want to understand which conformation was the observer there on the experiment. So we performed DFT calculations where of the gold 34 with 1 cysteine. In this case, we used the sweet ionic cysteine because it's the most commonly observed in water solution. And we have 3 options where these 3 possible isomeric rotational conformations are the ones on the, and if you can see, it looks very similar, but the difference is on the position of the, I think it's a gauche position against the sulfur, where it changes to hydrogen, nitrogen, and carboxylate. And then we take the possible combination, also taking into account the possible second site of the carboxylate. So when we compare the Raman's spectra with the experimental spectra obtained, we looked at the PC. It's the one which it's more close to the experimental results, but the pH, it's the one with the lower energy. So as a conclusion, it was like the PC or pH cysteine conformer can be the one that exists on the experimental results. But one because of the energetic, that it was the lower one, and the other one because the similarity observed with experiments. And also because there were some vibrations around this range, which are related to the amino group and the carboxylate group. That was the one that we focus more. Also, it's important to notice that at 300, we observe a peak that starts to appear when you have the complex, which is associated with the gold sulfur vibration expression, and also a red shift on Raman bands corresponding to the carboxyl group. It's observed on the other hand, and a blue shift on the amino group. It's observed also. Then, as the second one, work was to study the metal, how the metal ligand interface affects or is associated with the chiroptical activity. In this case, now we have, as before, we have the gold cluster with 2 cysteines in the case. And also we have the silver and copper clusters with cysteine. Here are the sizes of the nanoparticles observed. And in this side, in this part, we have the what is the absorption spectra and the circular decrease obtained with TDDFT from these models that we use. As we can see, there are good match between experiment and theoretical results, where we can conclude that the chiroptical activity is associated to the metal ligand interface, because this only recreates, like if I go a little bit back, it only recreates like this part of the metal ligand surface area. So this is the one that dictates the chiroptical activity of the material. Also, we analyze the main absorption bands, which are from metal, from ligand to metal in case of gold and silver, and from metal to ligand in case of copper. Also, in this work, it was the first time observed for the chiroptical activity of copper cysteine, which was not very good defined. We have very small intensities and a lot of peaks on the circular recurrence. And also, I didn't show that part, but silver cysteine was the one with the higher anisotropic factor. Then we now analyze the absorption of 2 cysteines on the same 34 atoms metal cluster, where now we have the gold, the one we had at the first time, the silver and the copper. And we want to understand the difference observed on the structural arrangement that occurs between the different metals with 2 cysteines. But it wasn't observed a big difference between them. It was only a small position that one has changed. And as in the first paper, we observed that in the 3 case, the interaction with the cluster of the cysteine is between the sulfur atom, and as a second site, it was the carboxylate. So this is in enrichment with the first case, where we studied the different position and the different combination of the rotameric isomers. But as it was interesting, you remember, I said like the PC and pH are the one, sorry, the P, I forgot that. Yeah, the PC and pH, it was the 2 possible options, as we see between comparison of theoretical studies and experimental results. But here we use the different combinations that we can have, and we observe that it's 1 PC and 1 pH, the combination that we have, that it has the best match between experimental and theoretical results, as you can see here in the comparison between experimental results, which is the black line, and theoretical result, which is the yellow, silver, and brown lines.
Any idea where the rather big differences, for example, at 1250 weight numbers in the KC come from? Are they related to the size of the nanoparticle, or to say that, I mean, one does notice some peaks which are really big in the experiment and not there in
theoretical results.
Theoretical results. Any idea where they come from?
Well, there is we use this model, but it's possible that the nanoparticle that you have in the experiments is a little bit bigger, because the nanoparticles were around. Also, you have a combination of sizes, because the range is going, I think, if I don't get it wrong, between 1 nanometer and 2.5, 3 nanometers. So perhaps it's this combination of different sizes of cluster. The one that you are observed on the experimental result, and in the other side, on the theoretical results, we only explored the 34 atoms cluster, which is the one that we think is the more closely related to the experimental result. So in this case, the Raman spectroscopy reveals that each metal modifies the spectrum in characteristic manner because we observe a small difference in the Raman spectra between different conformers that are related more with the atom that you have, especially on the region. We are expected to see the metal sulfur interact stretching band, which was going between, if I'm not wrong, 280 and 350, more or less. The nanoparticle sustained interface configuration are very similar between 3 nanoparticles. And as I say, the formation of the complex PCPH array is induced and mediated by the surface of the metal nanoparticles, which is the one that we observed from one side, more close to the experimental results, and for the other side, also the one with lower energy. And now, what is next? Right now, we are trying to go to a bigger organic molecule. In this case, the glutathione, which is a tripeptide. And it's analyzed also following some same methodology with gold nanoparticle. In this case, this one is only for the presentation. And also we want to try, or we want to try to observe the same molecule, glutathione, in a gold surface, because it was reported that it helps to block the beta amyloid protein, which is related to Parkinson and Alzheimer. So it is reported to work against this disease, to prevent it. Also, right now, one student is working on an anti-specific global search code, or at least that is the title that we have. Where we are trying to map different sites of the molecule. I mean, this is a cluster, and we're trying to map different sites and put a chiral molecule and to see which site is the best option. And but we try to do it on a systematic way, and not like maybe in the past it's used to be like by hand. So it's gonna be like some kind of Bayesian-Hopkins, but not like a Bayesian-Hopkins algorithm. Also, we are now trying to we want to explore also the Kerfman quantum dots, because this one it was reported in 2016, sorry, to exhibit by itself chirality, because the twist that it had exhibit some chirality. But also we want to observe from an chiral quantum dot to induce some chirality, in this case with some attaching to him some amino acids, which it was previously reported. And also in other case, like giving something like this, where the oxygen hydrogen gives the chirality to the molecule. Well, I want to thank to all the collaborations that we have. Here is Penelope and Alejandro from Instituto de Ciencias Nucleares UNAM. These two are the ones that are developing with some students the experimental work. Also, they are right now working on synthesizing the gold nanoparticles with glutathione. So this work is going at the same time, we can say like that. between experimental and theoretical results. Well, Ignacio, which is the head coach, we can say, and Andres Alvarez is a PhD student. Also, these three are Fernando, Jorge, and Cedric, which was working on the Physics Institute. These two as a student, this one as a postdoc. And these students, which are developing different parts of the world, Luis Manuel is working with the code that I mentioned. Juan Carlos and Diana are working with the metal nanoparticles with glutathione, and Natasha is working with the graphene quantum dots. So this is all for my part. Thanks for your attention. Thank you very much.
In the case of the experimental work, they don't seem to have the lowest energy structure. And all the theoretical people or all the people that calculate ground state, we claim that the most stable cluster or the most stable system is the one with the lowest energy. But it seems that the experimental results does not show that. What does the experimental people measure? Do you have any idea? Because we always claim that the most stable or the one that is going to show on the experimental measurement is going to be the one with the lowest energy. Nevertheless, the experimental results, it doesn't show that. What does the experimental people measure? ¿Qué mide la gente en los experimentos? Todos los teóricos decimos que el estado más probable es el de menor energía. Sin embargo, cuando se hacen los experimentos, no solo sino algunos otros más, como óxidos metálicos, no aparecen esas estructuras. La pregunta es, ¿qué miden?
Okay. I didn't understand the last word actually. Well, they are measuring the absorption, the circular decrease, and the Raman spectra, and related to the difference between the global minima and the one that we are showing that is the most related to the experimental results, can be associated to two things, I think. The first one, the temperature effects, and the second one, the chemical environment on the experiment, because these experiments are, and the characterization of the results, it's performed on solution that I didn't mention, but the second two works, we incorporate solvent effects with implicit model. In the first one, it wasn't the situation. So we looked that it can be a differentiation between the previous one and the next one. So actually, this one helped in some stuff like the glutathione. Sometimes when you make the optimization, if you perform it in gas phase, doesn't stable as a deuterionic molecule. But in solution, perfectly goes to deuterionic.
Yes. Well, in this respect, the first of all, of course, I mean, what you answer is that it was meaningless that what we are calculating as internal energy.
All right.
That's free. And therefore, it will be all the energy effect. Yeah, I don't get into account. But I mean, from the calculation, I think what we said is that is a really serious issue, right? Because if you have 60 in the superionic phase in the gas phase, it's unstable. It immediately goes into the neutral. Now you put the superionic case onto the cluster, but it is still in the gas phase. So you have cluster 15 superionic phase in the gas phase. My question is, when you then make a frequency analysis, Do you get only real frequencies, or do you see imaginary frequencies?
As I know, was only real frequencies.
But that's a little bit surprising, right? Because
Yeah.
if you would take the zwitterionic glycine in the gas phase alone, you never get real frequencies.
Actually, in that part, because that work was previous, that when I go into the group, I'm not very sure about some stuff, but as I know, was only real frequencies, and it was performed, like I said, in gas phase, as I know, but perhaps maybe I misunderstood some information about that.
Because even if you use an implicit, if I may, even if you use an implicit solvent model, you don't get the stability really of the zwitterionic form, because you're missing the water or the solvent molecules that are between the amine group and the carboxyl anion. Now you need a kind of shielding, electrostatic shielding. So you need something like either everything quantum mechanically or QMM in order to really get the zwitterionic as a ground state. So that is a little bit issue. And in the same direction, if you look at the different conformers of your system, PC, pH, and how you name them, how large is the energy difference between these conformers? Because they are only rotation of chemical bonds. So how large is the energy difference, for example, between a PC and a pH?
I don't remember actually.
These energies are extremely small. There's a range of 1 or 2 kcal per mole. So that is where the entropy effects come into the game. If you make it, if you calculate one of these conformers, in reality, as soon as you have a little bit of it immediately rotates and produces an entropic effect. So you can never get really you see in sperm.
Okay, next question.
Well, Andreas has asked already something which I want to ask about the frequencies and also the equation related to the different conformers energy difference of the system. So basically, I got the answer. I want only to say that system you use here for a specific application, generally for biological applications. It is quite rigid, a kind of molecules which is used to help to crystallize, for example, DNA fragments, etc. So the difference in energy between a second and we now, the difference in energy between the different components, as it was pointed out, should be really small. I don't want to.
I'm just curious. You said you were using a global or developing a global optimization scheme, which was similar to Bayesian hopping but not quite, for trying to find optimal positions and states, I assume, of your molecules on top of the cluster on the surface. Could you say a few more words? How the optimization proceeds and how it is different from Bayesian hopping?
Well, perhaps I say it wrong, I don't know, but I said that it's not like a basic hopping because previously I worked on a basic hopping algorithm, and there you have like the distortion of the cluster and something when you have 2 or more atoms, you have the swap of the atoms and something like that. That is what like the code was developed, but right now we are interested in keep it like it was the structure of both in this case the cluster and the amino acid. So we are trying to only make rotations around of the amino acid rotations around the molecule to explore the different possible sites of absorption and to compare between each other. And also if we have like for example 2 or 3 enantiomers, explore also those enantiomers because of sometimes we are expected to have a small difference. Actually, we are working only up to a very small thing.
What you are saying now sounds as if you have a rigid cluster, a rigid molecule, and then you move the rigid molecules on the surface of the cluster. So now, after you have made this rigid move, do you then relax cluster and molecule?
Yeah.
Yeah, so that's very much like in a way like you make long moves, and after every move, you make a minimization. And that's basically what basin hopping is. Right? I don't know, would you agree? Or
Almost. Yeah, that's actually, because we are working on this project only very small time. We are still developing very well. So we only have the big idea, we can say, because also, I mean, system, we know that it's anchored by the TO, but maybe later we want to explore another amino acid that we don't know in which site is anchored. So we want to need to explore different sites also. And there is some other troubleshoots that we are having.
In basin hopping, you will need to shake the molecule, perform local optimization, but then again, shaking, not moving, or the super. Moving is the same as the shaking. It's a big move you make on the energy landscape from one region, but in that case, the organic molecule can be attached to the same cycle after the shaking. I mean, the system is cluster plus molecule, right? So now we make a change, a big change by moving the molecule a long distance, and we minimize. So you have opt, that was the big change. You go into a basin. Some people will have a basin hopping. I think they would then say, do I accept the move based on the, say, Monte Carlo criteria, Metropolis criterion between the previous and the later basin you are in? I guess that's what probably the original basin hopping. That is a reason why it's points. Not exactly the basin hopping work, because in basin hopping we will need to change also the molecule. Not only even the displacement of the surface of the cluster.
And also in this case, I mean, in basic copies, that the isomers used to be different in stoichiometry sometimes, or also in the shape. And in this case, you are keeping the shape and the stoichiometry of all molecules. That was, I say, it's kind of different, but at the same time, it's very similar.
You have a limited move class, but the basic scheme, making a big move and then minimize, is still the same. I mean, you could stay at the same position, you're right, and have the molecule twist a lot. But that would be also a opinion. So that's why I'm just curious whether there was anything special in addition which came from that. Okay. Any other question or comment? In that case, we thanks Jonathan. Would you have any time for the coffee time? No. Start. Right.
This what?
So I was thinking if this was transmitted online.
No, it's start.
Can we start to make some
Implements the transition. We can directly use this.
because usually actually later.
Right, exactly. But you need to mix the yeah, we have to mix this and get some magnetic.
Why do we use no sensitive chains?
Because it doubles the electricity transition principle between the cables and the real system.
No, because it says from the little. One must have people that must have nothing.
But it gives you which are rather large. And the problem with this fluctuations
Therefore, you need to ask more strength.
more elements to change to make fluctuations here.
And how do one choose it? If we use 3 terms,
Well, this is
you can use 3 or 5.
the first use more than one. Actually, I put with my that you would have not believed, right?
Like,
You watch things because you watch them.
oh, yeah. Vamos a ver qué pasa.
No, despertar no, questo
Exactly.
Like you just could have told me, no, just make me a signal like this for 5 minutes.
It's a cellular I buy to hex the time. Yeah,
Just to understand.
it's an expensive starting.
No, I think you have, I mean, even more expensive than that. I think
But it's a problem. But it's just good. Rather harder. They use something like knowledge.
very expensive watches. It's like a master.
And there,
Like the Rolex are quite because I have used watches the Emirates, they have in Cape Cod, something like that, but every special edition buffet or in Paris. These are like a that's it's a useless amount of money for that.
Potentially, yes, the markets, and now the kid comes to the champions to provide
Exactly. Then you have Messi, Mbappé, Neymar. Yeah. Then you see really the people that here really exactly.
Gets much money. It's like that on sign that restricted to the sign, you know, some of the costs.
Like in Canada, is Canada said the time.
It's a schedule in the Canada is you can get 2.5. And if you want 128 ports
For 1 week, you know, fans there to get into it.
Entonces,
Well, they kind of feel and feel like how many months they got. Donde no me llegaba, se
I think in case of a building
they don't really like the way you
is the request for the for them and so they are going to be upset. It's the end of the day. It's all the politics.
and it's on your you're trying to buy more stuff and those things. And at some point you're going to buy that stuff.
Not all is
pero hay algo que el mantenimiento más que por eso y se tiene que ver, pero no
se puede ir por
pero se motiva uno que se va a ir de café gusto, le haga platicar, que haga atrás de alguna entrevista, primero una idea.
That's my argumentation. Points, which are, and then you can explain. And then at least I don't know how many possible that you then don't see actually that is instead of you can
Yeah, to take it.
And I mean, is this in virtual taking the children, but we don't make it stay office. Yeah, what the people in the government and the US, then also and don't matter. No, it's all the phone.
Forget it. What do they do? What do they do in this class? That's why you already have the cross.
This is why I think I'm because I think everybody else in the organization are able to makes sense. And so this is the thing I'm glad for them to be a hospital.
I see. Yeah. Yeah, because I know that you are. You're too young.
I'm going to say, I mean, 6 years ago, so the generalization of
Yes, mother
it's such a big size. Unfortunately, I mean, when you still something after those, they're going to be seen that like a little bit different time of I don't know. Advisory.
Yeah, this is some consultants.
They are such a position that they
Immediately,
yeah, I mean,
after 60.
I think I'm still going to my student development. I would like to do this. I would also think that I'm using in my because all of these platforms when you have to do it. It was
and then run with many notes and many. We started that relation every day. But it's losing more time. 1 week I have. We like to start with 1 week.
This is it's one thing where we read. It's a good time. Yeah, because after a week they start and it wasn't say a month, 2 months ago. Usually and you run out everywhere. And start every day.
Yeah, Alvaro told us that he's going to take a picture. I don't know if outside or he's not there. Well, before you start.
Okay.
No, don't move. No, he's taking care of himself.
I didn't grab my cellular.
¿Alguien tiene de cámara un messages?
Yeah.
Yo lo quería comprar para mí, de no por color morado, como quiero un playera.
No, nada.
Ahí no, como rosita morada. Nada en Virginius. Of this. No, this here. With this thing, you cannot move it too much. I think this thing will not be.
You make it with your own, no?
What is?
You make it with your own or something. Adesso non c'è una luce di sta. Senti, sei buono. So you put it in the dinner?
Yeah, I built it in here before.
Sì, corretto.
Sí.
También.
Ya se están viendo los dos. Sí, sí, es que mira, está muy bien. Me acabo de fumar. Yeah, sorry, I moved it because of Toronto.
Yeah.
If you move it in the middle, if I use the mic.
Yeah, but the problem is that we are broadcasting in YouTube.
This is mic. Okay, that's interesting.
Okay.
He needs his computer maybe.
This is the limiting factor.
Put it as little as possible.
Okay.
So I just simply on the data and maybe they can get.
No, you need to take care of maybe you can take your laptop and put it here. Yeah, maybe. What requires your laptop? You have only one. So you can change over there. Okay. And now
I'll take some light.
it's not bad.
No, this makes it. This is better.
Yes.
Okay. Don't forget to do it, Mike.
Don't forget.
To put the microphone.
Yeah. No, que ahora es Y luego, pero sí te digo, en la academia la memoria de los años de otros estudiantes de doctorado. Bueno, cuando yo fui a la normal, que había cualquier con todo esto de la periodistas bueno, y es lo que me ha estado trabajando. La verdad es que que eso sería bien, pero bueno, yo cuando es una sencilla, nada más que la así como que está no más ingenierías sino estructuras grandes, no ya no tanto el presidente, estructuras micro, una serie de una configuración de una pulgada, vamos a decir, ¿Cómo lo podrías poner para que también se forma de matar My grandfather
Tienen calor, tenemos los aires. También. No, tienen calor. Yo no tengo calor. Pero sí funcionan. Sí, prenden los dos. Que hay, vamos, no necesita bien, ya, sería. Pero yo no tengo cuadros. Muy bien, tiene que más sabio, bien por estar en el estilo, la historia. No, porque es un tema, no. Todo te digo que la normal es
que tengas el
ahorita aquí en la uni, bueno, fue utilizado con el a veces que saben sí, ya tienen sí, tener un minuto. Sistemas como candidatos a entrar al humo, pero también
Sorry, may I have your attention, please? The photographer from the university is here for taking a group picture. Can we set ¿Puede decirnos, yes, puede decirnos en qué parte? ¿Puedo buscar? Sí, yes, aquí adentro. ¿Cuál sería el mejor lugar para colocarnos? Fuera.
Ah, bueno,
Muy bien.
fuera. Sí, sí, sí. Dejaron computadoras y dejaron.
Sí, no me preocupes. Se están acomodando todavía.
Sí, sí, porque tienen cosas ahí. Están escuchando el apoyo.
Le cambiamos ahí una locura. Le mandamos poner una locura.
Está. Hace su mirada.
Sí, ándale. Más antes de que hay que dar.
Para la foto.
Sí, pues si las papas ya se le voy a decir algo que le hagan. De nada, que le den una colaboración moral.
Okay, the next talk is presented by Professor Dr. Andres. He studied chemistry at the Leibniz University of Hanover, and where he received his diploma in 1989 with a thesis work about aromaticism. And he earned his doctorate degree in theoretical chemistry
under the supervision of Professor Carl Jung. And he had a short research stay with Professor Roman Nelejewski in Poland, introduced him to the density functional theory. And since this time, he is involved in the technical implementation and development of the density functional theory called DIMO. And actually, his research in the Sindestar Center in Mexico, a titular professor position in theoretical chemistry.
Yeah, thank you very much for your kind introduction. I was advised to put the microphone on, which means I have a timer in my new cellular, which means that I'm restricted in my freedom here a little bit. So please positionate yourself in the form that you can see the slide. Okay, it's a pleasure to be here. I would like to thank Alvaro for the kind invitation. I would like to thank the full team here for setting up this really nice workshop. And when I got the invitation, I must say that it was a little bit unusual for me to speak again on cluster science conferences. The last one was in 2018, I think, in Switzerland at the Gordon conference. So I had quite a bit of fun to prepare this talk. And I thought that a title could be simple magnetic superatoms that might be of interest to this audience. This is a work I started with a really brilliant licenciatura student, Jorge Moreno, during the pandemic. And Jorge is really a brilliant student, or was a brilliant student. He could do anything. And he left me after his licenciatura for a position in industry. He is system administrator of an international company here in Mexico, and the salary did not compete with what a PhD salary is. So this is the outline of my talk, and who knows me, this outline looks very different to what I usually talk about, because I have only one slide about theory. And everything else is application, or at least application-oriented. So I hope you will appreciate that. Before I start, you have seen this picture, I think, already before. I would like to thank the DEMON community. This is a community of around 25 research groups all around the world that are devoted to the development of DEMON2K, an open source code we have developed since more than now 30 years. And the code has now something like 2,500 subroutines, 500,000 of line source code without comments. So it's really huge. And we have 3 gatekeepers who take care that the code somehow remains. And I have the pleasure to be one of them. I really thank this community for that. That was the last DEMON meeting we had in Freius, shortly before the pandemic. This was how DEMON meetings looked during the pandemic. I like this face. This is Mark Casida in Grenoble. He was really fed up about the pandemic. And we had good news, because we met again last year in person in Canada, in Calgary, actually, or close to Calgary, in Kamanaskis. We forgot to make a picture. So I took a picture from a DEMON meeting, something like 6 years ago, 7 years ago. We also had a Calgary. I also would like to acknowledge very deeply the listed funding agencies. There are some funding agencies which have supported the code development groups for more than 2 decades. And I think that is outstanding. And there are always ups and downs with funding agencies. Everybody here knows this. But I am deeply grateful for this possibility. So my first slide, my only theoretical slide is about auxiliary density functional theory. So auxiliary density functional theory is one form of DFT as it is implemented in D12K. So there's also Kohn-Sham DFT implemented, there's Hartree-Fock implemented, there are post-Hartree-Fock methods implemented, but ADFT implementation in D12K, I think, is quite unique, because I think it is in the moment the reference ADFT implementation, at least if you go to LCGTO developments. There is a reference implementation also for plane waves that is in Quickstep from the Parinello group. And but I think we are the reference implementation for LCGTO. So what is ADFT all about? So if you look at classical Kohn-Sham density functional theory, you know that you calculate two different systems. You have the real system, which you want to calculate actually, that is this one here, and you have a fictitious system, which is the so-called Kohn-Sham system. And in this Kohn-Sham system, you do something really perverse. You switch off the interactions between the electrons. Yeah, so you have non-interacting electrons, and there's a recent publication from the group of Levy where he actually builds a density functional development on top of these non-interacting form. So of course, this is completely wrong. So what do you do? Well, you must somehow tweak the external potential in such a way that the results that are coming out of these fictitious systems match with the real system. And the matching parameter is the density. So here you have the condition that the density of the real system equals the density of the Kohn-Sham system. And the magic of the exchange correlation functional is this manipulation of the external potential. So the exchange correlation functional does this manipulation of the external potential, and the quality, of course, of the exchange correlation potential is how is this manipulation done. So this is standard Kohn-Sham DFT. What is the difference to ADFT? Well, in ADFT, we are introducing a quantity which is called an auxiliary density. This is from the name, auxiliary density functional theory. And the Kohn-Sham density, or the real density in ADFT, becomes a functional of these auxiliary density. And now the issue or the trick here is that if you look at this density and you look at atomic-centered code developments, then this density is a quadratic scaling quantity. It's a density matrix P mu times mu from R times mu from R, and mu are atomic orbitals that are somehow located in space at your atoms. The issue here is that this auxiliary density, as you see it here, is a linear expansion. So what you trade is a quadratic expansion against a linear expansion. And of course, if the number of these auxiliary functions is similar as the number of your basis functions, then you save one order of complexity in your computational methodology. And that is the basic underlying idea behind auxiliary density functional theory. And this functional dependency has to be variational. That is a key aspect here. And this has been first worked out by Brad Dunlap in the form of density fitting. Now, if you look at the algebraic structure, and as an example, I show you here the ADFT energy, you can now appreciate the benefits ADFT gives you. And if you look here, this is the core energy, this is identical to Kohn-Sham. These two terms are now describing the Coulomb repulsion inside the system. And the most demanding computational term is this three-center electron repulsion integral. That is three centers because mu and mu are atomic orbitals. They are at two atomic centers. And this K bar is an auxiliary function on a third center. Yeah, so you have a cubic scaling behavior here, the vertical bar, the double bar here, this is the Coulomb operator. This kind of structure you also will find because it has been migrated from ADFT into Kohn-Sham DFT. So if you make density-fitted DFT, it's now implemented in some programs, or a very misleading term is resolution of the identity. I mean, if you want to make me crazy, then tell the resolution of the identity. This is the same type of Coulomb expression as you see it here in ADFT. But ADFT is not stopping at this part here. It also uses the auxiliary density for the calculation of the exchange correlation energy function. And this looks at first instance like a small change because you simply put a tilde over this row, but it has huge consequences because this quantity has to be calculated numerically on a grid. So if you have rho here, you have a quadratic scaling functions on your grid points. And you have many millions of grid points usually in your calculation. If you introduce here the rho tilde, then you have a linear scaling functions on your grid point, and you dramatically reduce the work at each grid point. From the computational implementation, it is very nice to see when you look at the Kohn-Sham matrix elements in ADFT. These are the derivatives of these energy expressions with respect to this density matrix element. When you look at these Kohn-Sham matrix elements, you see you have a core Hamiltonian. This core Hamiltonian is intrinsically linear scaling, even so it looks quadratically, but as soon as you use integral screening, this quadratical scaling goes into a linear form. And then you have only this term left here, where you see these are two sets of fitting coefficients, the Coulomb fitting coefficients for the Coulomb interaction and the exchange correlation fitting coefficients for the exchange correlation interaction here. And what you see is that these fitting coefficients are linear. They're simple vectors, because the density matrix is a quadratic matrix. And so this allows you extremely efficient parallelization. So Demon has scalings for a first principle code that are linear scaling up to 128 pores or more. This makes it quite unique, at least in the LCGTO community. And what we have done over the last 25 years or so, we have derived very efficient integral recurrence relations and asymptotic expansions for these three center integrals. So that already at the medium size of systems, and that is for me a system size of a few hundred atoms, these things become linear scale. So as a result of this setup, you see here the computational demand of a typical ADFT calculation. And this is a first principle calculation. And when you look at this, you see a large extent of these calculations, with 61%, goes into linear algebra. This is very much similar as if you do a semi-empirical ENDO calculation, NDVO calculation, or for example, if you do self-consistent or charge-consistent type binding calculation, you will see a very, very similar distribution of the computational time. The usually time-dependent parts, like the electron repulsion integral calculation or the numerical integration of the exchange correlation potential, you see is in the case of such an ADFT implementation, usually very, very small. Yeah. And so you see basically a computational demand, at least in the distribution of the computation time, very similar to semi-empirical methods. Of course, we have a larger computational demand because we don't work with minimal basis sets. We work with larger basis sets, which makes the matrices larger. But at the same time, you do not deviate from the Kohn-Sham accuracy. So if you compare and calculation, for example, with a PVE0 functional in Gaussian, with a PVE0 functional with ADFT and Demon, then you will typically see deviations in the optimized bond lengths that are below a tenth of a picometer, and deviations in the relative energies that are below a tenth of a kilocalorie per mole. And the nice thing is that all of that is variational at this stage, so you can formulate analytic derivatives. So this is the underlying methodology that allows you these kind of calculations you have seen in the morning, for example, from Patricia, where she does BOMD calculations of these clusters that are 20,000 or more time steps for each of these kind of multiplicities. Okay, so this was my theory, and this is what we will use in the following. And now let me introduce superatoms. And I know for some of you this might be super simple and oversimplified, but I'll do it for for these people who are not familiar with these kind of research lines. My favorite paper, actually, for the introduction of cluster science is this one from Knight and Walty Hare, where they measured polarizabilities of simple metal clusters, sodium and potassium, and they looked at the limit when you come from the bulk to the atom. And at the time when this paper was published, it was believed that this transition is smooth, so that you go in a smooth form to the atomic reference. But if you look here in the top, you see this is not smooth. This is everything else in smooth. And if you zoom in and you augment the experimental data with some newer experimental data, what you see is that you see here some characteristic behavior dips in the polarizability of the dimer sodium cluster and of the octamer sodium cluster. And this even at the very beginning of cluster science already pointed out that there is a connection of the structure of these clusters, of the simple metal clusters, and the electronics, the geometrical structure and electronic structure, they are connected to each other. Other experiments that are very, very famous are these odd-even oscillations in physical observables, like here's the ionization potential, or these characteristic high intensities in the mass spectrum of selected cluster size, very often called magic numbers. Remember, these here are cations, so if you count electrons, it's always one less. So these are 8 electrons, 20 electrons, 40 electrons, 58 electrons. So as I said, these experimental findings have motivated immediately in the early papers already theoreticians to make simple models. And a model that has turned out over the decades to be extremely, but extremely successful is the analogy between these clusters and atoms. And the analogy comes from the point that you build a cartoon of this cluster when you have an interior region that are basically the cations. Yeah? So the sodium plus ions, you put them together into the cluster structure, and then all the valence electrons, they are forming an electron gas around this cluster, very much the same as in metals in periodic extended calculations. The difference now is that you have a finite size system, so you have a finite size electron gas, and that means in the most simple case of a spherical geometry, you obtain such a set here of discrete levels. I'm a chemist, I would call them orbitals. The physicists sometimes call it one electron wave function. Use this word to drive me crazy. So for me, these are orbitals. And the characteristic now is that when you occupy these orbitals with electrons, you have shell closing. Very much as in the periodic table, right? When you go to the raw gas elements, you close shells. The helium, S2. Helium neon, S2P6. You have very similar characteristic here. And this is claimed to be the reason for these intense peaks you see in the mass spectrum. So this is really historical science, what I'm telling you here. And for us here, important is that there is an elementary, fundamental difference in this analogy. And the fundamental difference comes from the fact that in the atom, the nucleus has basically no extension. In all our calculation, we use the nucleus as a positive point charge. It's a mathematical point. It has no structure. But these cluster of cations, of these simple metals, have, of course, a structure. Yeah? And when you then look at these cations, at these cluster structures, you see pictures like this, very often in the literature. This is for sodium 4. So 4, so to speak, valence electron cluster. So it has an electron gas with 4 electrons. And these electron gases, 4 electrons, is a build of double occupation of an S-type orbital, so this is the S2 occupation, and the P-type orbital, which is P2.
And what you now see here is that the degeneration of the p-type orbitals, this degeneration in these clusters is lifted. And this is typically a Jahn-Teller effect, and that is the reason why when you look at the structure, it's not a square structure, it's a rhomboedic structure. And this rhomboeder is a Jahn-Teller distorted square, if you want to say so. This is fundamentally different to an atom. So if you have a 4-valence atom, for a chemist, that's carbon, S2P2. And if you think about the ground state multiplicity of carbon, it's of course a triplet, because you have the 2 electrons sitting in the degeneracy of the 3p orbitals. And by the stabilizing exchange energy of these electrons, the triplet is stabilized against the single. So you have the Hund's rule that you have when you occupy degenerated atomic levels, you occupy them first with 1 spin manifold. That is exactly what you see here. And this is the fundamental difference. And now you see already why this is for us important. So if I'm talking about simple magnetic superatoms, that seems to be a contradiction by itself. Because if you make Jahn-Teller distortions, you always quench the spin. And that is why you see the odd-even oscillation, for example, in the ionization potential. So, these, however, and this I can show you here, these, however, these occupations you saw there in the tetramer of the sodium cluster is sensitive to very small energy changes. What you see here are BMD simulations of the sodium-4 at 200K and 750K. So the energy you put into this cluster is really little. It's half a kilocalorie per mole or so. But if you look at these relaxations, you see here at low temperature, a relaxation in the plane, as you would think from the static picture. If you look here at the higher temperature, you see relaxation over 3 dimensions. Yeah, so that is a fundamental difference. And of course, we have electronic structure behind. So the geometrical structure is a result of the underlying electronic structure. Here you see the 2 highest occupied orbitals at low and high temperature. And what you see is that at low temperature, this s orbital is always delocalized over this full cluster of 4 atoms. And by this, it keeps the cluster planar. Here you see in this moment, for example, no, not really, that was just coming here. So, no, I'm overstepping it. But you see here correlations, you see here correlations between, like here, correlations so that you have the sp orbital correlating to 2 s orbitals and that you get 2 dimer systems. And then you have, of course, a possibility to rotate over 3 dimensions. So now, what are superatoms? And these superatoms are usually defined by some shell closing. If you look at our polarizability, now it becomes clear how to connect these dips in the polarizability with superatoms. So you have here the sodium dimer. This is a 1s2 shell closer. You have here the sodium 8. This is an S2P6 shell closer. Yeah, and it becomes also clear from where you get these intense mass spectrometer peaks. You count the electrons and you see here the shell closer. And what is for us important or will become important in this talk is a 58 electron cluster here, which is a shell closer in this simple picture. Now, at this moment, this is all quite exotic. We are talking about sodium clusters in ultra-high vacuum. So does it have anything to do with chemistry? And the answer is yes. This here is a chemical reaction, which is actually before chemistry. This is an alchemic reaction, where you have mercury 2 disproportionation reaction with elementary mercury to mercury 1. And if you want to interpret this, you can say that the formation of these dimercury dication is actually the result of forming a superatom in terms of an S2 occupation. You can make this more modern. These here are results from the late Castleman group in Penn State, where they constructed cluster assemblies from clusters that were charged, and they could then, by soft blending, produce such kind of cluster materials. And the production of these type of cluster materials then builds the bridge to really inorganic chemistry, to the very famous simple phases that were discovered in the 30s of the last century, and are actually in solid state chemistry something like these cluster assemblies. So there is a strong connection to chemistry. And of course, in the last, I would say, 2 decades, there has been an enormous work of ligand-protected superatoms. Kronberg is the name here of reference. But you have to be careful. You should not overstretch the concept of superatoms. And this here is an example for this. When we discovered the ground state structure of the palladium-13, Julio actually showed you it saw on some substrate a decade ago or so, we said the bilayer structure that looks like that. This is a superatom, yeah, because of the unusual structure that you don't have an icosahedral structure for 13 atoms. But if you look at the molecular or cone-charm orbitals, what you see is there is some tendency here of forming cluster orbitals, but there are also quite a lot of localized orbitals in this system. And this is typical when you go from the coin metal group, so the copper group, left to the periodic table. So this is the nickel group. If you go to cobalt, you see even less of these delocalized orbitals and more of these localized orbitals, and on iron too.
The ground state of the cobalt is the same structure.
Yeah, that can be.
No, it is.
Okay. I would not be in conflict with my interpretation. No. So this is something where you see that not everything that looks like a superatom really is a superatom. The other point where is more recent from us, this is this copper hydride, which you see here. If you look at these cluster structure, you say, oh, this is an interesting structure for hydrogen storage, because you have a copper cluster and you have hydrogen inside. But that is not true. As soon as you do a topological analysis, you see in this structure, there are no bonds between the copper. There's only one copper-copper bond, somewhere here in the middle, but every other coppers are bonded over the hydrogen atom. So if the hydrogen goes out, the cluster structure simply is no longer there. Yeah, this is a disproportionation reaction and it falls apart. So you have to be really careful with this concept of superatoms, not to overstretch it. Okay. So as I said at the beginning, with this discussion, magnetic superatoms seem to be a contradiction by itself. But you can think about a methodology to create these kind of materials or clusters by doping simple metal clusters. And that has been done for the first time, to my knowledge, in the group of Peter Liebens. And this is an experimental mass spectrum from him. And then you can do electron counts, and you can see that the number of electrons you have on the doped atoms changes with cluster size. And we have studied that in great detail. I would not like to go too much into details here, because you can do such electron counts, but you always have to be aware that these electron counts are based on models. And if you change the model, the electron count might change. The general thing, what you see is that with growing cluster size, you do have a quenching of the spin multiplicity in these systems. And I would like to only show you briefly that this idea of localized electrons in these systems is really not working. This is not reality. And for this, we are looking at these copper 12 vanadium and silver 12 vanadium cation. So if I go to the copper 12 vanadium cation, I take the icosahedral structure. What I find is this kind of occupation, and you see here an unpaired occupation of a 5-fold manifold. This is a 1D cluster orbital, and immediately you see a Janteller distortion here into a tetrahedral symmetry. And if you look at the single occupied orbitals and you look at these distribution of the orbital, they are not localized at the vanadium. They are distributed over the full system. You can see the same also in terms of the silver. So at this point here, I switch gears and I go to something that at first instance looks completely different from what I have talked about so far. And that is the melting of finite systems. So this has been published for the first time more than 2 decades ago by the private group, Haberland group. They were able to record such kind of heat capacity curves as a function of temperature. And by recording these curves, they were able to look here at the maximum, which they correlated to a melting temperature, and they could even determine latent heat for these melting transitions. This is a finite size melting transition. This is not a second order transition. Yeah, this has this shape because it's finite size. These are fantastic experiments. They are now done by Bernd von Isendorf after Professor Haberland retired. So the connection point I want to make is sodium 55 plus, because sodium 55 plus is somehow completely out of the road. These here are melting temperatures with respect to cluster size. So the cluster grows when you go to the left, the melting temperature grows when you go up. And you see sodium 55 plus has a melting temperature that is similar to clusters that have thousands of atoms. So very small cluster is a very, very high melting. And this result was so weird that there are 3 independent experimental measurements in the literature about these melting temperatures. And all of these measurements come basically to the same conclusion. Well, we have a melting temperature somewhere between 280 and 300 Kelvin, and we have a little bit less than 20 kilocalories per mole latent heat inside these transitions. So the idea, the challenge we had was to do this, verify this, or falsify this theoretically. And before I come to this, I underline that this is really surprising. And now we come back to our shell closer. Remember, sodium 55 plus is not a shell closer. It's not a particular stable cluster. Sodium 58 plus is a particular stable cluster, not sodium 55 plus. And unfortunately, there have been introduced in the literature the idea of geometrical shell closing. Fortunately, the community has rejected this idea to a large extent because it's really not consistent with what really happens here. Okay. If you look at the argumentations, all of these argumentations are really pointing to sodium 55 plus as a singular case, as something that has no equivalence in other cluster structures. So this is the setup for our Born-Oppenheimer molecular dynamics we applied to sodium 55 plus. The only thing what I want to say out of that is that we run individual trajectories at different temperatures and we glued them together with the multiple histogram method. So this was a big criticism. Over all these years, I presented this in the cluster community. The other point is that by this form, however, we had statistics that were some kind to 5 nanoseconds. So the statistic altogether was reasonably solid. The calculations are heavy and you need massive parallel implementations. So this is the outcoming, and focus first here on this curve. And the first outcoming was this red curve here. And when I saw the curves the first time, I was very happy because there was a parallel work of this with plane waves done in India by Professor Kanhere, and we found a very, very similar melting temperature. So I said, okay, this looks good. LCGTO seems to work. UMD works fine. So I sent this curve to the experimentalists. And I got 12 hours later the answer. This curve was 6 months of calculation on the West Britain country. And the experimentalists, they wrote me and they said, Andreas, if this is a curve you calculate, we would never be able to measure this transition because the curve is much too flat. They would not see anything. There would be too much noise in the experiment. And I said, oh boy. So that goes really into the limbo. And I had a couple of really hard weeks, I must say. But then we tried something completely out of the toolbox. We said, okay, what happens if this cluster ground state is not a singlet? It's 54 electrons. If you think about the quenching, the Teller distortion, and all of that, that should be even number of electrons, that should be a singlet. But what happens if this is not a singlet? And by some argumentations I show you in a moment, the quintet state is a possible candidate. So we took another 6 months of computational time on the West grid, and we calculated the quintet curve. And wow, this is what you can really measure. And Kanhere never published this curve because he calculated this curve here and there. And now I show you what is really the difference between these quintet and these singlet curve. Here on the left-hand side, you see shortly before the melting peak at 250K, here you see the singlet, here you see the quintet at the same temperature. And what you see is that at the beginning of these trajectories, this is only a few picoseconds, the cluster structures are basically the same. They are nearly equal. And it looks so that there is not much of a difference. But if you look at this potential energy curve, you already see that you have here an increase in the potential energy. And there must happening something fundamental. And that is what you see now here. You see here the distortion of this icosahedral structure that is statically, in static calculations, always an icosahedral structure to an ellipsoidal structure. And this ellipsoidal structure never ever finds back the icosahedral structure. Completely impossible. Whereas on the right-hand side for the quintet, you keep the icosahedral structure all along your trajectory. And only after a long time, as in terms of this simulation, let's say 50 picoseconds or even 100 picoseconds, the structure distorts a little bit from this icosahedral, also tries to become ellipsoidal, but immediately a few femtoseconds later, it goes back into the icosahedral structure. And of course, a very, very interesting question is this kind of breathing on the quintet surface, is this periodic? Because then what we would have here is a time crystal. Yeah, that is one of the points which you can see here. So this is a fundamental difference into the molecular dynamics of these two curves. And what you see here is that you get reasonable agreement with experiment. And also these here, this is prolate deformation coefficient. You see that we can explain from the singlet structure why we see this peak here inside. So bottom line is that for the sodium-55 plus, this molecular orbital diagram that you would have built on the basis of all the knowledge you have from these kind of simple metal atoms is wrong. And what you find is this Hund-type magnetic superatom. And I must say that when I had these results at this point, we did not publish. I felt very uncomfortable with this result. I said, okay, we have these individual temperature trajectories. The statistic isn't very good. And so based on these results, I can really not safely say that this is really a quintet ground state. So fortunately, the experimentalists had low temperature photoelectron spectra of these sets. You see these low temperature photoelectron spectra here. And in these spectra, you see this very, very characteristic shoal. And they already told, when they interpreted this spectrum, that this looks like a high symmetric cluster. Yeah, that there's high symmetry based on this photoelectron spectrum. So we simulate this poor man's style at the beginning with density of states, and this is a quintet simulation, this is a singlet simulation, and well, this is very convincing at this moment. For the experimentalists, when I showed them that, they said, also, the non-experts in this field, they said, okay, this is convincing. And with this, we could publish our results. When the paper came out, Bernd wrote me and said, well, Andreas, honestly speaking, if I tweak a little bit on the conditions of these photoelectron spectra, so raise a little bit the temperature also, I can get something like that. You need to do something more. This is not good enough. And fortunately, at that time, Vince Ortiz just implemented his symmetry-adapted propagator calculation. So that is solution of Dyson's equation. Yeah, so where you get the poles of the Dyson equation. And the sodium 55 plus quintet ground state is equal to dihedral symmetry. So that's perfect for him in the symmetry-adapted calculation. And he could do this rather expensive wave function reference calculation. And he found semi-quantitative agreement with the experimental measurement, and also his Dyson orbitals reflect very well the Kohn-Sham orbitals which we had from our calculation. So with this, I would say there is now a 90+% chance that sodium 55 plus really has a ground state. So, so then this would be the first simple magnetic superelement. The sodium cluster that behaves like iron. Yeah, or if you want, like chrome, actually. Yeah, unpaired electron, paramagnetic. This is the real truth of cluster science, that the elementary properties of atoms change by cluster size. And I remember you once again, these here are the orbitals of the sodium 55 plus cluster. And Peter Hackett always said, when he talked about cluster size, each atom counts. That's true, Peter, but I think even each electron counts. Here we have a system where when you only change one electron, you immediately get the Young-Taylor distortion. So really an electron count here that changes the structure and particularly the dynamic behavior of this cluster. These are the spin densities, and now I would like to come to the last part of my talk, and that is the search for new magnetic superatoms. So far, sodium 55 plus is an exotic singularity in all of this world of clusters. So is it really so exotic? Is it really so single? That is here the question, and this is something we undertook during the COVID pandemic. And we decided not to look further in the alkali group, but to go to the coin metal group, also for the reason to come closer to really preparative construction and preparation of such clusters. So we looked at copper, silver, and gold, and there are some general considerations. I think many of them are quite straightforward, but I would like to point out here two situations or two issues that are really important, particularly when you look in the literature. So we calculated silver and gold with quasi-relativistic and relativistic corrected effective core potentials. We use the Stuttgart Grace component. And the usual kind of knowledge in the community is that these valence orbitals that are coming with these effective core potentials, they are huge enough for the calculation. And what we figured by comparing simple diamonds is this is not true. Yeah, so for silver and for gold, you must augment the valence orbital space substantially. We are using here Dunning basis sets in order to get reasonable bond lengths. And it turns out that these bond lengths are critical for the establishing or non-establishing of magnetic superatoms. Yeah, so that is one point here I would like to to point your attention. So this is basically the challenge we had. This is the Born-Oppenheimer molecular dynamics we have done already with quite effort, but now we have to do molecular dynamics of these systems. This is something which still is open, and we would like to do this in the not so far future. What will help us is that we do have almost linear scaling for the parallelization of D12K now to reasonable size, of course. So we scale for this clusters almost linear until 128 cores. And I like the slide from Postivo very much of the weapon arsenal. We also have augmented ours. And the new weapon we have inside is parallel tempering, D1V. This is implemented in a double-stage parallelization. So we have the normal parallelization for each replica calculation, and we have the parallelization for the replicas themselves. So this is the possibility to provide or to do these calculations with easily 1,000 or more cores with almost linear scaling. And the really nice part is that we now also do have replica exchange inside that, so that the constraints that the molecular dynamics are temperature separated, we can overcome. Yeah, and of course, when you do something new, then new problems arise. And I would like to show you one problem here, and that is we now incorporate into our molecular dynamics this replica exchange high temperature trajectories. This is a trajectory of sodium 55 plus at 500 Ks. And what you see in this kind of trajectory, of course, is that you have evaporation, that you have cluster fragmentation. How do we take this into account in a correct way? You see already here, that doesn't look really right. This is with an Anderson containment. So for this reason, we have developed over the last years quite a bit of molecular dynamics confinements. We have the soft quadratic embedding potential, which probably for this application is the method of choice. But we also went to QMMM. So we have a complete setup of QMMM in D12K so that you can embed such a cluster into an environment. And one of the ideas here is direct simulation of collision-induced dissociation experiments. That is what we would like to do here, where we have then an inert gas around our cluster, for example. We have a fundamental problem for this. We do not have found so far a satisfying solution. We have good ideas how to do this. And that is the wrong dissociation limit you have in single determinant approaches. That is a very old problem, very well known. And one of the ideas, what one could do is if one goes beyond the Coulson-Fisher point, this is where these two curves are separating, that you introduce symmetry breaking solutions into your ADFT or DFT calculation. This must be done in form of an automaticized form. So this is something we are working on, and we are searching actually students who will help us here in that work. Because there is some interest here in the community on global optimization, I also would like to point out that parallel tempering BOMD is a good, at least partial ingredient to global optimization. You have seen this form of global optimization Patrizia showed this morning. And what we have done recently is we work with active machine learning. And one of the topics here is to combine machine learning with parallel tempering BOMD for global minimum search. We have done first steps, and we see that there are certain advantages, but there are also disadvantages of such a machine learning approach. And so this is something we are also quite interested in. For the photoelectron spectra simulation, I'm still buzzing with the comment of Bernd. I can change this shoulder. So we want to implement temperature-dependent time-dependent ADFT. So we have first developed time-dependent ADFT very recently. You see that we do have reasonable good accuracy, and we have, of course, excellent performance. This is standard TD-DFT. This is timings for TD-ADFT. That is a contribution from Luis Ignacio. He is just on the way to finish. And he has done already first temperature-dependent photoelectron spectra. We did this here on the C60. And what you see, this is the blue curve actually is a calculated spectra at 600K, and this is the spectra calculated at 0K. You see that the temperature has an enormous effect on the peak position. It's much larger than the intrinsic error of TD-ADFT for valence excitation. So if you compare TD-DFT calculations without putting in temperature, you might do huge errors. Yeah, much larger than the intrinsic accuracy of this methodology. So where we are in the moment, so we have optimized these clusters. We find the typical singlet quintet this difference, and what we really find is that we find quintet ground states, of course, for sodium 55 plus and also for copper 55 plus, but not for silver and gold 55 plus. There's a ground state, at least in this icosahedral type structure, is distorted icosahedral type structure, is a singlet. If you look at the binding energy per atom compared with the bulk, and you see also that for silver and gold, you do have larger differences. So with this one, I'm finishing. You can read the conclusions by yourself, and I'm more than happy to answer your question. Thank you for your attention.
In one of the movies that the last movie that you have shown, that one.
Yeah.
You find, say, fragmentation of the cluster instead of evaporation of particular atoms.
Yeah.
Do you know why is that? Is the temperature you use, or what is? Because in principle, evaporation of atoms would be easier.
Right. Honestly speaking, I cannot answer you the question. My feeling is that we are in the wrong dissociation limits, because this is a calculation on the singlet. So this is a restricted calculation. And if you then look at the dissociation of an atom, you are much over the dissociation limit. So this is one of the problems exactly where you would need to go to unrestricted calculations, and you would need to introduce symmetry breaking. Yeah, this is exactly the point you said.
So follow-up comment to this one. I mean, I'm not so sure I would expect even single atoms to evaporate. I mean, we have done studies on clusters using energy landscape exploration and so, and there we do find breakups and not that single atoms drop off. Often the broad breakup is actually not so bad, and so this did not surprise me, this picture.
Okay, also, it surprises me, I would go with Julio, for the very simple reason that we had studies some 20 years ago of copper clusters, okay. And we joined the Mainz cluster group at that time, and they found single atom evaporation out of copper clusters and diamond, sometimes diamond evaporation, but that's it. Only single and diamond evaporation. They never found really this type of fragmentation. And I think this type of fragmentation is simply because of the underlying electronic structure is simply wrong. Okay. I would guess. But
because I actually for this the first time I was thinking, we have studied also, as I said, the sodium clusters in the past, and it's probably to remember that sodium clusters have the spin multiplicity alternation between the singlet and doublet. So I would have expected in this, it was pointed out the fragmentation with atoms, dimers, etc. And there you should have this in terms also this multiplicity alternation between open and closed shells, and the needle, the electronic structure we are using is not adequate to reproduce this.
One should be careful here, not to make it. Also the electronic structure method is adequate definitively around the equilibrium structure. There's no problem. The problem is really when you go beyond the Coulson-Fisher point. Yeah, here. You see that this is the kind of dissociation you find in a restricted methodology, but it's even worse. If you do unrestricted calculation, you find the same. And the reason for that is because your start density is symmetry adapted. So this is H2. So the symmetry adapted start density will always end you up here. So you need something that breaks symmetry. If you want to do this, you usually use single triplet instability test, which is a diagonalization of the TD DFT matrix in the RPA. And then you can see that you find the imaginary root, and that tells you that your solution here is not correct. But you don't want to do this, right, in a board of molecular dynamics, because you would have to do this at each time step. That would be simply crazy from the computational demand. So you need something much more simpler. And in fact, this green curve, which is a correct dissociation limit, I simply found by twisting together the start density in a way that you incorporate the symmetry breaking into start density. And to make this systematic, that is, in my opinion, the way how you could solve this problem in general. And we have shown this not only for H2. We have shown that this works for O2, which is very complicated. We have shown it for N2. So we can use this for single bonds, double bonds, triple bonds, you name it. And but in the moment, it's a lot of handwork. You really have to build the start density correctly. That has to be optimized. But that would be the first task for an PhD student. I don't know.
Have you checked the spin contamination during this project?
Spin contamination is usually very low in these structures. We have done ROKS calculations also for the static calculations for the sodium 55 plus in the quintet state, and we see the same qualitative energy following as in UKS calculations. Interestingly, what will change this are hybrid functions. As soon as you want to do your calculation something good, as some people here did, so putting in B3 or M06 or PBE0 or whatever, you will bias towards the high spin structure. And you will find then that silver 55 plus ground state is a quintet, which is an artifact of the hybrid function.
And how is handled the multiplicity of the fragments in that case?
This you really can't say, because the full calculation which you do here is restricted. So this was sodium 55 plus singlet, and the full calculation is restricted. And so this is why the dissociation here is definitively from the electronic structure point of view.
I guess in a way, I thought about this earlier when you talked about the fact that you had found later, you found the sodium quintet case. Now, I mean, ideally, one would want to do, I would think, your search in an unrestricted way, so that the system by itself could decide whether it goes for quintet, triplet, singlet, or whatever. And I remember trying to do this with quantum espresso for some solid system, and it didn't really work.
No, we did this. Not for the sodium 55.
But I was wondering, whether this works with your method.
Yeah, we did this very recently. I think it is published actually here in this TCA for Green issue. And it was done on a much smaller cluster, because the machine learning implementation at this moment is not so good. It is actually external by Python script. And we optimized the spin state simultaneously to the structure of this MO4C2. And this in fact works with active machine learning. quite fine. This is one of the includes spin state optimization. That is one of the benefits of these machine learning.
And if I don't have machine learning, then will it show silver?
Naja, it is a setup of how do you want really to do the calculation. You have to do then the different multiplicity calculations separately from each other, and you have to look how these things are then going energetically, for example, in a molecular dynamics or in a genetic algorithm. We have tried this long ago with palladium-13, but honestly speaking, also at least with palladium, you would need spin-orbit coupling in order to get decent results, and we don't have in the moment the implementation of a two-component SCM. So in spin-orbit coupling perturbatively, as it is done in coupled cluster, also will not help you. You need it so consistently.
And then my final question there in this context was, if you start with your singlet state, and then you say, okay, let's do local minimization, but I let it be unrestricted. Is the singlet state going to be stable, or is it going to transform on its own to the Jahn-Teller distorted?
No, the quintet state is not Jahn-Teller distorted. The singlet state is Jahn-Teller distorted. The quintet state is imposable, right?
Okay.
I mean,
the other way around.
the other way around. Yeah, the point is when you do a quantum chemical calculation of a finite system, that in that moment you are giving the spin multiplicity as an input, right? So what you could do is you, for example, you optimize the singlet state, which is Jahn-Teller distorted, and then you say, okay, from this structure, I now do the quintet optimization. That is, I think, what you're asking for.
I wanted to do so to say, at each step, I wanted to have the system try to find the optimal atom positions plus
the spin multiplicity. Okay. The question, the question is how you technically want to do this. What is your step? For example, if it is a molecular dynamics step, you can in principle think about that when you do these kind of parallel tempering, BOMD, that these replicas not only are different in terms of the temperature in which they live, but also in the spin state. That is something we haven't yet implemented, but it is at least possible. In the implementation that has run, this is here the machine learning implementation. This is with the genetic algorithm. So the step here is I don't know, the combination or whatever. Exactly. Interestingly, what you have here is, in order to make this really working, you have to give the spin information in copies, because you do have much more structural information than spin information. And in order that the active learning really takes care of this correctly, you must balance these two. So what we do is we give the spin information not only one time, but we give it 5 times or 10 times. And then the active learning does it rather good. Yeah, it's quite a black box. It's quite a miracle of machine learning stuff. Okay. Questions from yo puedo discutir en español, no es muy bueno, es en Spanish, pero no es posible. No lo sé, los estudiantes tienen algún comentario o una pregunta o algún resto.
What calculation would you like him to do for you?
Okay. Well, okay, I will not discuss it. Yeah, please.
Okay, I will say this in Spanish.
Sí.
¿Usted cree que es prometedora la inteligencia artificial o machine learning, deep learning, para incorporarlo en el estudio de cúmulos?
Yeah, Can I answer in English? Okay. Also, what you do is the machine learning part, first of all, obtains a set of structures. So you give some structures to the machine learning. From these structures, you train, for example, a neural network. Yeah? So you have the many body tensor representation of your molecule. It's an input parameter and it's an output parameter. That's the energy. So, and when the training is satisfying, that means when the kernel of the neural network is satisfying and adjusted, you say, okay, now give me predictions. And then the neural network gives you structural predictions. Then you take these structures, put them back into D1, and locally optimize the structure. And many of these structures are really crap. You throw them simply away. Then you get a new kind of generation. You again can do some genetic recombination on the structures. You train again your neural network with these modified structures. And what turns out in the active learning is that the training process, the cycle by cycle by cycle, becomes less and less inhuman. Yeah, and that is the exploration of the structural space by the neural networks. That is really the key ingredients that you obtain or that you can get from this active machine learning. Yeah, okay. No more. So then I'm ready to go away from here. Thank you very much for your attention.
Pepe, ¿quieres usar el computador? Pues
Sí, se prefiero. No, de aquí la traigo. ¿Qué conector te sirve?
Sí, sí. Vamos a hacer de manera.
¿De A o el de
Yes, you're lots of people who like it a lot.
Un poco desinfectado. No, lo que le decía yo en usted dice pequeños los personajes que tienen que ver con la guerra, eso lo decía. Sí, sí.
Perfecto. Te pones el micrófono.
Restricciones holonómicas.
You know.
Okay, the next chart is presented by Dr. Jose Miguel Mendez Alcaraz, and it's about colloidal and clusters.
Thank you. Okay, I'm going to speak about colloids, but not atomic colloids. I'm not sure if my colloids are in the right place here, but Alvaro invited me. Thank you very much for that. So any plans, because my colloids are not atomic my cluster, right? Not atomic cluster. Please, any plans to colloids and atoms are very different. But they have, in the case of cluster, they have a common border, which is really not diffuse. And in that border, both things coexist, not in the tile and in the kind phenomena. For example, there was talking about that in another kind of phenomena. In this map here, we can see where I'm living. Atoms and molecules are living here, and colloids are living all over here. And humans are living here on the right of this picture. And there are molecules like the Na, for example, which are living in different scales in the more range of scales where colloids are also living. They start here in the primary structures, and this structure is living in the same scale where molecules and atoms live, and colloids not. But then we have the secondary structure, and tertiary structure, and the quaternary structure of the DNA, and colloids are over there. In the border here, both atoms and colloids coexist. Colloids are clusters of atoms, and they have very similarities in this region. And I want to speak, I have written a little bit of the language about those similarities in that region, because that is the only way I find to put my talk in this congress. And well, they are very different, and we can see here how different they are. The atoms have the lengths of angstrom, colloids in the nanometer and micrometer. They are materials, but not nanomaterials. They are mesomaterials. And the time scales can be also very different. Colloids have time scale for milliseconds, minutes, or hours, and the atoms have move really very fast, and ballistics. The energies are also very different. Here we have energies of electron volts, and here of the order of the of the thermal energy of the systems, and it can be 100 times smaller than this one here. A very, very important difference is that mostly the atoms, the structure of atom made of atoms in the scale of nano materials is mostly energy driven, but the colors are mostly entropy driven. That is a big difference. And these are quantum systems. The colors are classic systems. And here we have a fundamental interaction, but that is not really true. I have seen the other calls that you are using also effective interactions. In colloids, we have always effective interactions, and we can also model interaction that doesn't exist. And if we don't find an interaction we have using our calculation measure, we can cook it. We can synthesize systems with those interactions, and the motion of the atoms is ballistic in a classical sense, and the colors are always diffusing, subject to fluctuations dissipations than theorems. And the colors assemble self-assembly assembled in a natural way. So we don't have to do anything. We can look at the colors and the forms of complex structures. And the atoms need sometimes a little bit help to assemble. Okay, they are very different, but they are also similar in many sense. Due to self-similarity and the scale invariance of the system. And what I did with the following: if you write let us think about the working with ensemble theory, and we write the partition function for a complex mutual particles. And we have now that partition function. We integrate some of the components of the mutual in the partition function. At the end, we have again an integrated, a reduced partition function, which has exactly the same form of the initial one. The only difference is that at the beginning, we have interaction potential between all particles, and at the end, we have effective interaction potentials between the surviving particles. That's the same difference, but the form of the partition function is exactly the same. And any theory derived from the partition function on that properties is changed. Any theoretical expression derived from the partition function doesn't change the form when we integrate part of the systems. That property is very important, and it goes very often after some theoretical approximation. We almost always need to do some calculation, but in the initial form of the theoretical expressions, in the general initial form, they own that property. And in that sense, one expects to see similar properties when we are working at scale or at a large scale or another much larger scale or a much larger scale, as far as we are in the realm of statistical physics. When we live between the kingdom of statistical physics, we don't have that perspective. So staying here in the realm of the statistical physics, then we can expect to have some similarities between atomic structures, for example, and colloidal structures. And that has been used in the past very often and very successfully. I have here, for example, one very recent picture of the crystallization of salt. And we can see that out of the atoms move very fast. The crystallization dynamics is slow. Here are seconds. And we have here a colloidal crystal. And the colloidal crystal and the colloidal and the atomic crystal have very much properties in common.
we can start with the same, the dynamic of the structure is the same. If we want to see, for example, the dynamic of the effects in the structure of the crystal, it is the same in the colloids as in the atom. Well, here are also a picture of atomic clusters, and here are a picture of colloidal clusters. Colloidal cluster and colloidal crystal are much more easier to be observed because we can use cheap optical microscopes and it is easier to study. So we can use the colloids as a model to study properties of atomic systems in this case where it is difficult to see it. But we can see the same at a larger scale with more simple experimental setups if we use colloids. And this analogy, and like all analogies, it's at limits, but it is very useful also where it is true, where it is valid. And you can see, for example, in this paper here, a review about how to use colloids as model system for metals and alloys. Atomic alloys, not colloidal mixtures. And of course, atomic gases, liquids, and gels, and glasses, etc., have very much in common with colloids. And colloids are also used as model to study that kind of molecular or atomic systems. And in the dynamic, they are also similar. Think about an atom moving in a system, in a gas, for example, with a lot of other atoms that are exactly the same as the atom we are looking at. And it is moving ballistic and hitting other atoms. It will be continually hitting by other atoms, and in between it is moving ballistics. But after a long time, we don't see that ballistic motion. We see a kind of Brownian motion because this central atom, a long time after the beginning of the motion, feel the other atom as a kind of solvent, a kind of medium, which interchange energy with the central atoms through dissipation fluctuation theorems. And if we do molecular dynamics for an atomic liquid, for example, we have first ballistic dynamics, and a long time we have a diffusive behavior. And if we do Brownian dynamic simulation for colloidal system, we have diffusions dynamics from the beginning, but when the atoms start to begin in a diffusive form, they behave exactly the same. Also in the dynamics, they are similar. If we are in very, very long times. But it is not always that easy. In colloids, we have hydrodynamic interactions, and we don't have hydrodynamic interaction in colloids. Those are the interactions between particles due to the solvent in which they are dissolved. And they are not conservative interactions of very, very long range. They are the interaction with the longest range we know. And we don't have them in the neutron system. So it is not always that easy as in this calculation. This calculation was done without hydrodynamic interaction. But they are similar in many aspects. So let me tell you a little bit about colloids. I like this. Colloids, colloid domain is where physics, chemistry, biology, and technology meet. I think this is true. There is a book that with this name. And there are suspension of solid particles in a liquid solvents. That is the definition, the classical definition. But they have many properties which are the same properties of more complex suspensions. For example, liquid and liquid, gas and liquid, gas and solids, And that's why many colleagues use colloids as a general name for that kind of suspensions. The size of the colloidal particles is of several nanometers to several micrometers. The only thing important is if they are very small, it is not possible to distinguish them from the solid molecule. Then we don't have a suspension, we have a solution. So they must be larger than that. And if they are very large, they can be in solution, they sediment. So they must be smaller than that. That is the only restriction. And then we have a colloidal suspension. And they interact, they are subject to Brownian motion, that's very important. They interact with a lot of different interactions, either hydrophilic. And we can link some, for example, about cubic particles which have interact in a different form when the faces come together or the corners. And this is a fantasy model, and we can synthesize it. There are colors to do exactly that. That is possible. And we can, it is possible to synthesize a new material in that one. Mesoscopic material, not dynamic material. And the name colors, Thomas Graham named the colors the first time, and the name colloidal soft matter was the first time used by Gerhard Nagel in this book. And to have an idea where are the properties of colors coming, think about 5 liters of paint. In 5 liters of paints, you can buy that in comics. And you have more or less 1 kilogram of polymer dissolved in small particles of 200 nanometer diameter, more or less. And in this 5 liters. And if we calculate the surface of the interface between the polymer particles and the solvent, the surface is about 15,000 quadrat meters. It is huge. And that's why all properties of colloidal system are a product of the interface between the colloidal particles and the solvent. That's why before the people began to use soft matter system or colloidal soft matter system, they use interface physics, because the interface between both phases is determine the properties of the colloidal system. So now I'm going to speak a little bit how we model colloidal systems to arrest the colloidal particles in clusters. Not every interaction potentials allow that. We need a kind of interaction potentials which with the name competent interactions potentials. That I see there are interaction potentials. We have a repulsive path, a long range repulsive path, and then an attractive well closer to the particles. And this repulsion is not to Pauli process. It is impossible not to have the exclusion Pauli process. Then when the particles come together, they interact like these forces, which come from the Pauli forces, which is modeled here in this kind of potential with this part. And then we have here an attractive well, which we can change in the deep and in the range. And it can be due to van der Waals interaction, or we can dress the particles with attractive polymers, and we can manipulate. And in the front of this attraction, we have a wall, a repulsive wall. We model here with this form, but and it is due to for example, electrostatic repulsions. You can interaction with the electrostatic nature. Or due to, we can also dress the particles with repulsive polymers and very long repulsive polymers, and we can have this kind of steric repulsion between the particles. So we don't care very much about having a fantasy interaction with, because we know many of the properties of colloidal suspension depends on the qualitative form of the potential, not on the details. And in many cases, it's possible to synthesize such kind of interactions. And for example, it is relatively easy to produce an interaction that looks very similar to this one, using entropy-driven depletion process in a mixture of colloidal mixture. It is really easy to have a potential like this. Okay, we have done a potential like this. The parameters we have is epsilon, the dip of the attractive well, and the lambda, the width of the attractive well, and A times epsilon, the amplitude of the repulsive well. We will maintain fix the value of epsilon. That is not important. What is important is beta epsilon. We will change the temperature, and in that form we change the product of beta times epsilon. And we will change in our calculation this length and the height of this parameter. And we have colloids. That means the dynamic of the colloids is diffusive. It's described by the Langevin equation. I write the Langevin equation for the colloids. This is the mass times the accelerations. This is the interaction due to the solvent, the friction due to the solvent. This is the interaction between the particles, and this is a fluctuating force due to the dissipative fluctuations theory. This is a conservative force given by this time, and this is the interaction potential between particles. And we can escape these equations. Okay, in an overdamping dynamic system is zero. We can then integrate this part of the equation to get the position at different times of the particles, and then we can scale of quantities in this equation with these scales for length and time and energy. And at the end, we start with this equation and we end with this equation where the only dependence of temperature is here. And that means if we decrease the temperature of the system, what we have is that the motion of the fluctuation of the particles is smaller. They move shorter distances when the temperature decreases. And this is responsible for the arrest of the particles. If we decrease the temperature more and more, then the particles become arrested, and we are looking for arrested particles in clusters, and that's what I will show you in the next. Okay, we write an algorithm. We start with random initial configurations after 1 million cycles simulation and 10,000 particles, more or less. We thermalize the system with an initial temperature, and then we start to decrease the temperature in quantities delta 10 in more or less 100 temperature steps every time we do 1 million cycles of the simulation until to reach a final temperature. And then we have the final configuration where we can do statistical analysis of what we have. There are typical values. The algorithm is very simple, but the implementation is demanding.
Why don't you, so to say, start with TF star and just relax right away at TF star? I'm not quite sure what's the meaning of the initial temperature. TI star.
This is the temperature of the system at the initial, at the beginning.
But it's a real temperature. It's not the fictitious.
No, the real temperature.
10 million degrees or something.
Yes, but the scale, but it is the real temperature. But we don't know how is the structure of the system at that temperature. So we generate a random configuration, and that is not the right the structure of the system for that temperature. Then we have first to let the system run, the simulation run, and then we get the real structure for that temperature. And then we go further until the system arrests. And at the beginning, the system is liquid. At the end, it is a rest. And we want, what we are looking for is the particles are become arresting in cluster formations. That is what we are looking for. And the algorithm is very simple. You can, it's really very simple. But the implementation is demanding because we have to do that a lot of many times for many particles. It is demanding for physicists. It is not for theoretical chemists. Your algorithms are mastermind.
The final configuration will depend on the cooling rate.
Yes, because it is a configuration of non-equilibrium. Yes, but we do that slowly so that we get always the same kind of structure, not difference. With larger sheet, we can have, for example, before we have clusters, we can have a gel or a glass, which are random. So liquid-like structures in but solids. They don't. The particles are arrested. They don't move. So, and then we do statistical analysis. Statistical analysis, for example, the distribution of clusters. S is the number of particles, and N is the number of clusters which have that number of particles. And we can multiply this. This is this quantity, and if we multiply this quantity times S over N, we have a normalized distribution. Only because it is normalized. There is no other reason to do it. And so we can calculate how many clusters we have of a given size with 10 particles, 5 particles, with 100 particles. And we can also calculate the duration values, like in the polymers, and that gives us an idea of the size of the clusters. And from the duration values, we can obtain the fractal dimension of the clusters. When the fractal dimension is 1, we speak about a cluster which is linear. When the fractal dimension is 2, we are speaking about a cluster which is like a two-phase, and 3 for very, very compact three-dimensional configuration. And if we have values of the fractal dimension in between, then we have structures in between. For example, a spherical distribution with poles, like a cheese. That's which cheese. Okay, and we can also study morphology, concentration profiles, radial distribution functions, and mixed qualification and a lot of other things. We did all those calculations, but I don't to show that here. I want to keep the focus on the cluster structure. And okay, it has been actually, and we do that for colloidal systems in holes, in contained porous media. Yes, contained pores, in spherical pores. And other persons have done that already. There are a few papers about the clustering of colloidal particles in containers, in funny containers, in 2 dimensions, for example, or these are colloidal particles confined to in spherical harmonic walls. They interact with the walls like strings. And in 2-dimensional, that is realistic because we can't trap the particles with optical traps. In 3-dimensional, that's more difficult. But they do that. They did that for 3-dimensional system. it's okay. This they use the same potential I showed before, but this L is or A, the amplitude of the repulsion, and this alpha is of lambda, the length of the attraction, and this is the volume fraction. This is a dilute system. It's a concentrated system. When we have when they have dilute systems with these parameters, they have clusters, cluster formation. If the system is very concentrated, they have gels, a kind of gel, a kind of gel. This is a cluster formed by all particles in the system with a very fine structure, a very porous structure. This is a soft structure. They don't change because the particles are arrested in those positions. And we have here, for example, this kind of worm-like structures. But all the publication so few, 3, 4, which studied the formation of clusters in confined columns, show only the visualization of the structure they get. That is great because those structures are really very interesting. But we do now a little bit statistics using those structures. But we put the colloidal particles in a hole, in a porous, but it is not soft, it is hard. So we have less variables to control and to study the influence of the confinement and of the parameters of the interaction on the structure of the clusters. And we use this radius for the confinement. We use 10,000 particles and this initial temperature. The system is liquid with this temperature, and this final temperature where the system is always arrested. And we change the length of the attraction and the amplitude of the repulsion, and let all other variables fixed to study the system. And the result I'm going to show you are the results of a collaboration with José Saúl García Maldonado and Josué de Santiago Sanabria. Josué de Santiago Sanabria is a professor of CIVESTAR who is working on cosmology. And he is using this kind of analysis to study cluster of galaxies. And I think if it is possible to find a link between colloidal clusters and cluster of galaxies, it should be possible to find a link between atomic clusters and colloidal clusters. I hope so. And José Saúl García Maldonado was my PhD student, he's reading now. And he was working on the structure of colloidal liquids, confined colloidal liquids, to develop a new method to measure effective interactions between colloidal particles in a nature. But on the way, he discovered a huge interest for colloidal clusters and told to me, Pepe, I want to do colloidal clusters, not more liquids. Okay, let's do that. We were working on colloidal cluster at the time. Now he's now in the industry making data science and money. And I'm telling these stories about colloidal clusters. PhD students are great. Well, we start with a system where the length of the attraction is really very small, and the amplitude of the repulsion is changed, can be large and or small. And for this attraction, which is very, very deep, there are particles that come together, but really only few. The clusters are very, very small. And we can see here the distribution of clusters. We can see that the most of the clusters are only one particles. Only few are this logarithmic. That means this here is very much smaller than that here. And some clusters have 2 particles and others have 3 particles. No cluster has more than 10 particles. They are very, very small. And we can calculate the direction radius and the slope of this quantity is the fractal dimension. And the fractal dimension is really 3. That means they are very compact 3-dimensional clusters. Not, there is not interesting there, not interesting. And the reason for that is that and so the competition of this potential have the same following effect. The particles to come together have to jump the repulsion. That is not easy, but sometimes it occurs. And if they find a attraction well behind the repulsion, they can stay together. Not always, they can also separate due to the fluctuation, but they can also stay together. And another particle will come, and these other particles can jump the repulsion, but now not the original repulsion. Have to jump the sum of the log of both repulsion of the 2 particles. And they can do that, and they stay in the attractive way. But after when we have a lot of particles together, then the repulsion is so huge that it is not possible for other particles to jump it. And then we have a cluster. And when the attraction is enough attractive, the cluster is stable. If not, the cluster can dissolve. And that's why that kind of potential, the name of that kind of potential are competitive potential, because they are competing with the types. They are very funny potential.
For you, then, the cluster is actually a group of atoms which have like an empty space around it, which keeps them separate from the rest of the system.
We use the definition with it usually in colloidal science. That is, a cluster is formed by the particles which are separated by a distance smaller than the width of the attraction. That is the definition we use. That is usually in colloidal systems. It is possible to use other definitions. Okay, now we increase the length of the attraction. And what we get is the following. We have that it is very unlikely to have small clusters. And it's also very unlikely to have large clusters. But there is a size of the cluster where it is very, very likely to have particles distributed in those clusters. That means the confinement filters select the size of the cluster. If we do the same calculation for an open system with that confination, this curve is flat until some value, and then it decreases abruptly. But it is flat at the beginning. In an open system, it is the probability to have clusters of different sizes until a cutting value here somewhere. It's the same. We have a distribution of different sizes of clusters. But when we put those particles in a hole, in a pore, then the effect of the confinement is to select one size of clusters. And this is a logarithmic graphic. That means the probability to have cluster of this size is really very, very much larger than the probability to have smaller or larger cluster. We have really a selection of the size of the cluster. And we can also calculate the dilation radius. We can see that for small clusters in this part, the dimension, the fractal dimension is more or less 3. That means they are very compact clusters. And for large clusters, here, we have again a fractal dimension about 3. That means the clusters here are large, but very compact as well. And in the middle, the intermediate clusters, where the cluster grow from small to large clusters, they don't grow, increasing the size and maintain and keeping the fractal dimension. They grow with a fractal dimension which is more or less 1. That means they grow like one. And that is really funny. It is not possible to see that here.
las coloraciones?
The particles with the same color are of the same cluster. Of course, we have to repeat colors because we have more clusters than colors. And if we increase again the length of the attraction, we have larger clusters, very well defined here, but here we can see this worm-like structure. They start to grow and to fill the volume, and they do that like worms. That is maybe because of entropic reasons. I don't know. We have to study that more carefully.
I'm still a little curious. I mean, when you say the big clusters,
yeah,
do the big clusters contain many of the worm-like clusters, or are they spatially separate?
They collapse. They collapse. Here are spherical clusters, then worm-like clusters, and then the worm-like cluster collapse and form a bigger spherical cluster.
That's what was my question
Yeah.
earlier also, whether they are isolated spatially or whether they actually on one level you look at them and yes, I have looks like I have small clusters and I have many small clusters connected. I have the worm structure and then I have many worms getting together and I'm having the big clusters. Is that the correct picture or am I?
That can happen, but you can also have only one worm with collapse in itself. And form this is one worm and then it collapse and form a compact land. That can also happen. And we can also have clusters.
José, ¿no? Se está cambiando el tipo de fuerza. The driving force is changing from entropy to energy with this process, because somehow you have a sort of crystallization on the right hand side.
Yes. When you decrease the temperature, the energetic contribution for the free energy becomes more important than the top. At the beginning, the topic is not important. Yeah, that's true. But when you have mixtures of hard particles, colloids of hard particles are involved. They have, if you change the volume of a colloidal mixture of hard particles, the internal energy, keeping the temperature, the internal energy doesn't change. It changes only the entropy. So all the physics produced by a change in the volume of a mixture of hard particles is entropic. And you also find the same.
Well, this analogy that you have with atomic cluster, it is because this miracle cancellation of the entropy effect.
I don't know what you mean.
I mean, there is some regime where the entropy is somehow cancellation. There is a sort of miracle cancellation of the entropy. And the driving force is again the internal energy. Is that right? This analogy that you started with in the beginning of the talk, you start with analogy between the atomic cluster and clusters made out of colloids.
Yeah.
I mean, it is because the entropy is getting less and less important.
I don't think so. I don't think so. To link entropy with order, with visual order of the system is wrong. Often it is possible to crystal crystals increasing the entropy in colloidal emission. I think it's a competition, entropy and energy, and sometimes wins entropy, sometimes wins the energy, and most of the times there is a combination of both, which minimizes free energy, and that is likely what is happening here. But I don't have here the calculation for those quantities. To calculate internal energy is very simple. The energy is a microscopic variable defined by the configuration of the particles, which is really very simple to calculate. But the entropy is not a mechanical variable. It is an ensemble variable. To calculate entropy is very, very complicated. I don't have calculation for the free energy. For the energies, yes, we use the calculation for the energy to be sure that the system is thermalized. But the entropy to calculate entropy, that's not very right. So I cannot say the entropy behave like this in this situation because I don't have the calculation for it. And okay, and we can see the same, and so the confinement select a size of the cluster, but the difference I touched before because the parameters are different, and we also have three-dimensional very compact cluster here and here, and when they grow like this. Okay, if we do that calculation for open system, this is flat here, this is flat here, and we have a similar behavior here, but the growing behavior is like surfaces. The dimension is 2. The particles are very compact for small clusters and very compact for large clusters, but in between they grow like surfaces, not ones. These are also three-dimensional systems that I can find. They have to find a form to fill the confinement in a most efficient way, and they do that forming worms. And not surfaces. In open system, they form surfaces. They have no problem to expand. And okay, so final remarks. The cavity filters the cluster size that doesn't occur in open system, and the intermediate cluster of intermediate size will in one shape. This is a new result which has been observed before, but it's the first time that we do statistical analysis of those results and find that they dimension exactly that. What is expected for a linear distribution of particles. And this is really a very interesting result and unexpected because in open system the distribution is flat. And not here. And I think that's enough.
Let us suppose that Conacyt is a very well behavior, it has a very well behavior and gives you money to calculate the same, but in a square, in a cubic box. Will you expect the same type of results? What I'm trying to say is, what is the role that the surface or the internal volume of the cavity you have, how much does that induce the type of order that you observe? Will this result depend on the boundary condition you impose on the system?
Yeah, very strong. Stronger for smaller systems. When the core is very small, the particle have to distribute according to the form of the boundaries. If it is large, you have a very strong influence on the border, but in the middle, not so much.
In the case of galaxies, you have an open system.
Yeah.
And then what will be the link between this calculation?
No, there are clusters in an open systems, and what Josue is doing is calculating radial distribution function of the distribution of galaxies. And from the behavior of the radial distribution function, it is possible to have an idea of interaction between galaxies. And it is, one can see, it is not a system in thermodynamic equilibrium, but nevertheless, it is possible to have some idea. And from the behavior of the radial distribution function at short distances, it is possible to see the gravitational interaction. And for larger distances, there are funny things there. And Josue thinks it is dark energy, dark matter. And I don't like that very much.
Energy oscura, materia oscura.
Yeah. I don't like that very much, but it's the calibration. We have to accept what other person thinks.
For the presentation, anything about the certainly the fact that you have this spherical words is a main key for this algorithm, because you need this confined space. I must myself, what would happen if the confined space will change, maintain the same shape? I mean, changing the radius of these spheres, somehow we will impose, if you want, a kind of a pressure also to the system. Have you done this kind of investigation to see how the cluster selection will change?
That's a very good question. And I don't know work on that direction in confined systems.
Okay.
But there are persons and colleagues working on that direction in open systems.
Yes.
In open systems. And the influence of pressures on the or of gravity.
Yes.
Or gravity is really very important.
It would be very important in this case. I think you have all the machinery to eventually. I don't know if but I saw the questions you thought were are very simple. Just by changing, the radius, you could eventually compare which cluster size you obtain, and from there you can extract the information. Integration is important or not.
Yeah.
It would be quite interesting to see.
Yeah. There are people who do that for open system, not for confined. There are people in the international. How's the name of this station? In the space. There are people there working with that experiment. They have colloidal suspension there and are looking how the colloidal precipitation form crystals and form clusters in a microgravity situation.
It's a very nice presentation of it. You destroyed some of my fundamental beliefs and gave my first question is more technical. If I understand correct, you basically set up your system, you set up a certain temperature, and then you run a molecular dynamics, which is around. Okay. When we run molecular dynamics, the first question I always get is, what is this energy conservation? What is this momentum conservation? These conservative quantities. Is this in your kind of dynamics an issue?
Well, if you run molecular dynamics, you have to put attention on that, on the conservation laws. But you also have to link the Newton's equation of motion with the laws of statistical mechanics. And that means you have to force the particles to have a Maxwell distribution of velocities. And through this distribution, you get the entropy in the system.
Okay. Yeah, I'm wondering if one could transfer some of these techniques to the atomistic scale, because we are running basically as in our dynamics in the moment, everything constant. And I have the feeling, I cannot explain it physics, my physics is not different, but I have the feeling we do this in order to be on shorter time scales, to see things on shorter time scales earlier. Because that what you showed there was that in one of your slides, you said, okay, there are differences in the way of how a system evolves, if I understand correctly, at a certain time. And this was a long time scale. Then the systems become equal. I think what we are doing is enforcing explicitly these conservation laws, is that we want to come earlier to this point where the systems behave equally. And I'm wondering if we could learn from you, from this statistical approach, ways of how to really incorporate entropy, for example, in this melting of clusters and in this melting of single molecules in the right way. I'm not so sure that we do this right.
I think in the molecular dynamic simulations with a thermostat, you have included entropy. Because you have the laws of the statistical mechanics inside of your calculation. But to have it there and to take a value out can be very different. All things can be very different.
Exactly this point is where I wanted to go. I mean, for example, if I have my real system and I have my thermostat, the exchange between the thermostat and the real system of heat is non-directed.
Yeah.
But if I do this without any kind of manipulation, I violate momentum conservation in my real system.
Yes and no. That's what is the reason? What is the reason of the in the formulation of Boltzmann of statistical mechanics? You have sorry, I have to think it in Spanish. The postulate of equality of probabilities.
Yes.
And what is the origin of that equality of probabilities? That is the interaction of the particles with the thermal photons fulfilling all the space.
Yeah.
Yeah. And at this energy scales of those thermal photons, you don't have conservation. You have conservation only if you consider explicitly those photons, those thermal photons, in your expressions. But we don't do that. We do that in an effective form, accepting the equality of probabilities.
Yeah, but the point is, if we don't do this in our molecular dynamics, so we say, okay, now the momentum can be not conserved in the short range.
Yeah.
We never converge. We need to run the molecular dynamics, not nanoseconds, but outside the scope of what we can run. So the question is there a methodology that basically joins these two extremes together? On one side, we have the momentum conservation, on the other side, we have the correct statistical description.
I have to think about that. I don't know.
It's super interesting for us.
But I think this is a technical question.
Yeah, this is
in Brown and dynamic we have problems when we have hard particles, because the discretization of the Langevin equations is not valid. The name is Herman-McCammon algorithm. It's not valid for hard interactions. So what we did here is we do Brownian motion, Brownian dynamics for the particles, except for the step where they hit the wall. And exactly for that step, we solve analytically the Smolkowski equation to get the solution. But we cannot use the algorithm for this step because we lost all that properties. This is a technical question.
I have two comments here on the best of the discussion. One of them is you can, to the same, introduce temperature in a very realistic fashion. For example, if you look at the behavior of atoms on the surface by, so to say, heating the bottom of the substrate. So the bottom of the substrate, you really enforce the temperature. And the rest of the system is then going to adjust. So there will be time delays and all these kind of things. So that actually works quite realistically. So in this case, you have really explicitly in the region of the simulation where you don't care about momentum conservation, so to say. There you introduce the temperature, and for the rest of the system, it has to find its own temperature. And then the question concerning hydrodynamics, I seem to recall, correct me if I'm wrong, that in the past 10, 15 years, people have been using hydrodynamics concepts in the study of electron gases in solids. I mean, there's, I would have to take a look at the literature, but there is a certain amount of hydrodynamics of electron gases in, that's probably the purpose of conductivity and things like that. So there is something there, but it's recent. My impression is it's a relatively recent development in that regard.
What I can say to that is you're right, and it's a fluctuation precipitation theory is used for the derivation of the running physical image in the becoming zero. That's relatively old, which is 20 years old. Quite standard
somewhat. This is kind of hydrodynamic stuff. I haven't used it myself, so I only know it. I have a very stupid question. The pictures on figure 16, on page 16. I assume that. Oops, okay. I assume that, you know, the data points you have, that they don't come from a single run, but they come from many runs. Yes, right? perfect. So how many runs enter the purple, for example, the purple circles? How many runs do you use to get those data?
It's 40.
40.
40 runs. That is the reason of the dispersion today. From some runs we have a point, from other runs we have another point. 40, yes.
So it's,
We use very intensive Chicote.
We have also a kind of a curiosity question. Okay, with this cluster size, you see that they are formed. Within this approach, have you the possibility to estimate or follow eventually the change in the average temperature of each of these cluster sites or their instantaneous temperature during all what happens in this spherical walls?
Yeah, we assume that the temperature is the same in the wall volume.
You fix the temperature,
Yes.
but the temperature will remain always the same. No, my question was if there would be the possibility to look at this.
Gradients of temperature the same. That would be very interesting.
Yeah, that was my question, because I'm impressed when the cluster race, not there, in that moment you see a cluster size, you can have track. But it would be nice if you see this as a kind of formation process, not of a specific cluster size.
We don't know very much about colloids out of equilibrium. That is there are a lot of open questions in that direction. And that is the direction in which we are moving, but very, very slowly. Slower than the colloidal particles.
Okay, thanks. I was very interested.
No pueden hablar peor inglés que yo, así que con confianza.
Por ejemplo, a mí se me ocurre preguntarte por ello. ¿Cuál sería una aplicación o algunas aplicaciones
de los
sistemas confinados?
De los clusters, de los sistemas confinados en general. Yo estoy I'm working which application we can find for confined colloidal system. I'm working, for example, in a method, developing a method to measure effective interaction. When we have colloidal mixtures confined in a spherical coil, and we look only two of those particles. And you can calculate the value distribution function between them, and the profile, the density profile in front of the photovoltaics. If you can invert the body statistical equations from using distribution functions theory, exactly, analytically, you can obtain the effective interaction potential. That is very hard to do. The questions are simple, but very, very hard to do. And that is a possible application.
I think we must put the questions now because it's late.
Thank you very much.
Yes. Yes.
Ya hacía tiempo que no me sentía tan fuera de lugar. Pero es divertido.
Hablaste de cumulos. Hablaste de cumulos. Ah, sí, yo soy bastante.
Ah, gracias.
Y que no vayas a tener problemas. Ahí estaban mis acuerdos, ¿verdad?
Sí.
Eso es muy
¿Se llega caminando?
No, está por el lado catedral. No lo vamos a apuntar las de
Hijo de su-